spending quite a lot of time just opening the damn PCB file. Here we are. Let's see. And we also need schematic, of course. And we need to see what we are connected to. We are connected to PB12, sure. Though, if you're actually thinking about doing embedded professionally, I think Arduino is kind of weak, unless you're doing some like ESP32 stuff. There, Arduino can be useful. So if you are very serious about being an embedded developer for money, you should go either, like, not either, find a niche, because embedded has quite a few niches. For example, ESP32 or Bluetooth devices, like NRF microcontrollers, or like hardware like STM32s that I use, for example. Or maybe you would like to work with like analog stuff, or maybe like digital signal processing. So find a niche you like and like do like hard learning for this niche. Because otherwise, if Arduino is your cap of your skill level, you will struggle a lot to find the work. Because Arduino was never really respected as a skill level for actual work in embedded. And even more so now when AI exists and it can generate your Arduino code like in an instance. I applied an Nestle R&D in firmware, so still waiting. Oh, Nestle has embedded branch? Like Nestle that does chocolate bars, right? This Nestle. Oh, very interesting, very interesting. I didn't know that. Never know that they have such a thing. So PB12, and let's see our peripheral file. What do we have here? Okay. Okay. Sure. So let's go here. They apply electronics in chocolates, so they track you everywhere. Sure, sure. Sounds legit. Damn. Corpo. But like, if they have electronics job or like firmware job, I would imagine that they should have something like industrial automation job, like PLCs and stuff, not the embedded like Arduino. Because I would imagine they have factories and they need to automate factories, and factory automation is done using PLCs and industrial controllers and stuff. And this is quite different from Arduino actually, and requires a bit different skills, but not really, but kinda, depending on like where you're look from. So what I was looking at here, let's see. Okay, we enable GPIO A's. Okay. Then we enable GPIO's B's. Okay. And we do not enable interrupt, sure. So interrupt is not enabled here, right? No. PB12 is set up as GPIO input, but I don't see an interrupt enable. So let's implement it then. This is what we need to do first. Okay. So let's say we will have static inline void setup 20 as interrupt. Like this. The only way is in a firmware working. Oh, I mean, at the time you need to learn outside of your studies. You can't know everything. This is true. This is very true. But you cannot apply to a job. At least, like, I'm not sure like your situation because you didn't explain it enough. But in general, I don't think you can apply for a job you don't have any skills for. Like, it doesn't make sense. You will almost never get a job, especially like this, like today. I would imagine it was easier like a few years ago, you can lie in your resume and just get the job. And if the company is big enough, you will get training there if you're like smart enough. But it would be very hard here if you don't understand what you're applying to. But I'm not sure. Like, I have no idea about your situation specifically. So who knows? Maybe like you will be Gucci. Okay, so we need to enable our interrupt on the PB12. So let's go and see RGPO example, because we do enable interrupts here. Okay, this is kind of a lot. Take in, but we will not have a trigger. We enable the interrupt register, sure. Here, let's open our reference manual because we will need it. So reference manual for STM32G4. Here we go. And let's go and see our register. What with AI, you can do anything today, barely. That is kind of not true. But when we talk about very beginner stuff, like entry level, yes, you can do almost every entry level task you can imagine with AI. But when we go past the entry level, AI starts to struggle a lot. So no, I don't believe the project like this can be built with AI fully. I would never imagine that you can, at least with current level of technology, that you can build a project like this with AI. I don't think it's possible. So I also need a datasheet for the driver. So let's open it. And let's see, because I need to know what happens when the error comes. Okay. So let's read on our unfold. Fault indicator output, the pin is put logic low during a fault condition and requires an external pull-up resistor. Okay, so it put logic low. So we need to enable an interrupt on the high to low transaction. Let's give it a try. Let's give what a try? AI? Trigger rising. No, this will be trigger falling. So this is the setup we need just for the correct output, which will be output 12 in this case. And this will be output 12 to enable. We will check the registers shortly. And this is our interrupt handler. But you need cloud subscription. You do. Though, like, what are we talking about right now? You need it for what exactly? So okay. So this should be probably 3 then. This will be 4. Correct. Okay. So let's open the registers and see what we are changing. If you want to try to develop with AI, I do have a cloud subscription, and I can tell you for a fact that this project cannot be developed with AI fully because I was using Claude to analyze this code and to make very small parts of it. And I know that it struggles sometimes. And like one of the bugs that were introduced by AI when I was testing is an ADC bug that I was trying to solve for 2 hours. And with Pro subscription, it actually ate all my tokens and couldn't solve the bug. So it was such a pain in the butt. It was very annoying, actually. So I do use Claude from time to time, but I do it mostly for like renaming stuff, from moving stuff around. And I also find it's very nice to give Claude the code after the coding session, like 3-4 hours coding session, and say like, do I have any errors or do I have any bugs? And Claude is generally useful to analyze your code after you've done like quite a lot of work, and it's found very interesting bugs quite a few times. But no, I don't use it to generate code from scratch. I don't think it's a good idea. It is a tool after all. at least in the current state of the technology, it is a tool for embedded. Definitely nothing more than that. It is not a developer, even a junior level. It can do impressive stuff if you put the conditions right, but unless you put the conditions right, it struggles. It struggles a lot. So, register. Okay, we're here. Right? This gen. Are we here? This configuration enable. Sure, we are. Let's see. XTCR register. What it does is these bits are written by software to select the source input for. Okay, so we need to set PB12. And to do this, we reset this PC. So we need to use PB here because we would like to use port B for 12 interrupt. And then let's see other registers. Okay. FTSR. I think I missed it. My bad, my bad. FTSR. Not this one. Oh, it's a different peripheral. Sure, my bad. And the peripheral is called XTI, which is where exactly? Let's see, let's see. Okay, let's go one by one. No, 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 no. No, 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 no. No, 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 no. No, 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 no. No, 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 no. Here. Perfect. So registers, here we are. Let's see. So FTSR and IMR. IMR says what? Interrupt request for line is masked. Perfect. So what we need to do here is I'm 21. Hello. Our line will be 12s. Correct? Unless I am mistaken. Yes, so first 15 lines are for GPO, so we will need line 12. And I think this should be first thing we write to rather. And here is falling trigger. And we need falling because we need from high to low, right? Right, so the falling trigger for pin 12. Very nice. And we enable correct interrupt. And now we need to do interrupt handler. And to see how the interrupt handler is named, so we don't need our documentation anymore because the setup is correct. To see the interrupt handler name, we need to look at our startup file. So let's go to our startup file. And let's see. So XTI 15 to 10 handler, sure. Let's add it to our main and let's add it after everything, I would say. So it's just an error handler. So this will be a void. All interrupt handlers are a void, of course. Void, void. Here, what must happen here? We must check what interrupt happened and we must reset it. So actually, we'll still need our documentation back to see the source of the interrupt. So let's see. We have event register. So software interrupt on line X. User is enabled on this line. Writing 1 to this bit when it is 0 sets the corresponding pending bit, resulting in an interrupt. So this is the way to call the interrupt by software. We don't need it. Pending register 0, no trigger request occurred. 1 selected trigger request occurred. So this is an interrupt pending. Do we need to write anything? This bit is set when the selected edge event arises on the input line. This is cleared by writing 1 to the bit. So we need to clear this, I would imagine. I would imagine that this is what we need to clear. So let's say if, right? One moment. Yes, it definitely is. So if xti dot pr1 pr1 and our mask, which is xti pr1, and this will be if12 if12. And if this is positive, which means that this bit is set, we need to clear this, of course, right away. So we will write xti pr1 equals, because it is, hold on, it's read clear. Hold on a second. Hold your horses. See, we read clear. Software can read as well as clear this bit by writing 0. Writing 1 has no effect. Software can read as well as clear by writing 1. And this register is, yes, it's cleared by writing 1. Perfect. So we just need to do this. And this will clear this bit. This means that we handled the interrupt successfully. And here what we need to do is we need to call our function. It will be DRV8320 s, and the function name, oof, where is it? I don't see it actually. Let's go back to the file and check where the function is. It is called handle and fault interrupts, and it should be present. Why is it not? Oh, I see, because it's called differently. Okay, okay, it's called like this, sure. And we need our instance, and we only have one option here, which is device dot DRV. So this should work perfectly. And now we need to implement this part. And what will we do here? Actually, let's not open it. Let's open our documentation and see our errors. What errors do we have? We read the register, which is called fault status. So let's look for it. Fault status. Two different words. Yes. Okay, so this is the register description. And let's see, we have 11 errors, it seems. Do we actually have 11 errors? Do we have 11 handles here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And this is, why is it doubled actually? Was, what is that? Delay after last message is needed to guarantee proper communication. And why do we need to do this? Meow meow. Debu, how are you doing? This was not my best meow, but you got the point. Okay, so fine meow. Perfect, perfect. Finest meow on this stream. I actually have no idea why do we need to do it twice. And given that I have no idea, let me actually remove this for now. Maybe we will need to do it twice, but now I'm not entirely sure. And also it seems like we have more errors to handle. One more. Unless I am a dumbass. So let's see what this returns. It's just a read register, which will return us what exactly? Oh, it will return us 2 bytes. Sure. 2 bytes are more than fine. Okay, let's go back. So how are you doing, Nilaboo? Okay, so we have 2 bytes and we separate them into the errors. In what order? LC, HT, LB, HB, LA, HA. Okay, correct, 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 correct. And we have another bit which we don't check. So what is this bit? Let's separate it currently. Fault status and DRV8320 fault bit. So if this is the case, we need to do something. Return. Okay, so now, first of all, we need to log errors. And for this, we need to include our debug interface. Let's see. Debug utils. And we will be able to log errors. And let's see how we will log them exactly. How will we do this? How will we do this? Let's keep looking into documentation to see the descriptions. Logic OR of fault status register mirrors L and fault. Okay, so this is not useful because we use interrupt. So it just says that error exists. Okay, sure. Says read only, sure. Indicates VDS over current fault on the A low side MOSFET. Sure. Okay, can we somehow react to this? Can we somehow react to this effectively? Let's first do the logging and then we will think about it. So let's say we will use a code 41 as the base and let's be 0. Let's actually remove the return because returns are now damaging, not helping, because we would like to log as many errors as we can at the same time. So let's do this. Oh, oh, like that. And let's keep going. Sure. And sure. So now we logged any errors that happened. And let's see which are the critical ones. I'm not sure what overcurrent fault means and if we can do anything about it. But also, I would imagine that this function has to return something. So let's say it will return. Hold on. In case we are. Wait, hold on a second. Is this stored anywhere? I do believe that the error register should be stored or returned. And I would imagine that we can return it. So let's return this value. Because otherwise it makes no sense that this function exists, given that... Oh, actually. And if we return, we might as well not do anything here because this is breaking my architecture. So actually what we have to do it correctly is to just return, and this will be the whole function. And after that, we will manage it differently. I think this will be architecturally correct because current implementation is architecturally a mess. So you int 16T. Okay, and then let's see, we move this code out just with correct indentation, and we return our fault status. Fault status. So, okay, this function then calls it, and now we have a struct that stores errors in our device. So let's actually add a field to this struct so that we can store these errors and handle them on a device level. So device.h, we have our accumulated errors. Accumulated errors is not a correct name, but for now, let's keep it like this. And this will be DRV8320 as errors, faults. And we need to set it to 0, of course, during initialization, whenever this is. Where is it? Hello? Oh, it's even not even here because all of them are 0. This is fine. So we set our device errors dot our faults to this. And now we can analyze this. So we know for sure that error happened, that some error has happened, and we need to do something about it. And also let's remove the debug utils from here because they are not needed anymore. And let's go to our device and add a function to store the errors. Okay, okay, okay. What function do I use to actually store the encoder errors? Let me quickly check. I don't have any function, so let's actually use it as well. We might as well do the function for this. Right? Da, 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 da. Should we? Should we do it like this? Okay, let's keep it for now. And let's actually not put this into a function because I also need to think about the design, how it will be designed properly. So let's use this instead in here. So how will we replace it? We will use a space after this. And maybe I replaced a bit too many things. Let's see if it builds. I'm not entirely sure. It does build, it seems. We are in incorrect view. It builds. Sure, perfect. So now this makes a lot of sense. We lock all the errors and we can handle them on the device level, not on the level of the library, because library can be used on any device. The libraries, the way I designed them, they can be used on Arduino, on ESP32, on like any microcontroller from any family, and therefore they do not, or rather must not, include any code that is platform specific or implementation specific. And my debug utils are implementation specific because they are mine, because they are following the approach I developed. So it is incorrect to do these checks inside the library if I want library to be usable by other people as well. Here, the question arises, should we stop the motor? And I would say that yes, that if the faults happen, we need to stop the motor. So let's do it. It will be disable driver, just like that. Because if something is overheating or stuff, so we are in big troubles and we might as well just stop it. And now, let's read on the errors and let's see if we have anything useful to do with them. So overcurrent on MOSFETs, I have no idea how they are determined, and therefore what to do with them. Over temperature shutdown. So driver is overheated, so it can be disabled safely. This is proper behavior. Under voltage lockout. So under voltage can happen when? For example, if our power supply is lab power supply and our motor draws too much current and voltage drops due to this because we hit the current limit, right? Hold on a second. Yes, we hit a current limit and the voltage drops on the power supply. Okay, so this is useful, and if this has happened, we also need to disable the driver. This makes sense. Gate driver fault. Not sure what this means, but if gate drives are faulty, we might as well disable the motor as well. VDS monitor. What is VDS monitor? Exactly. The VDS monitor are configured based on the worst case motor current and the RDS on of the external MOSFET as shown in the equation. Okay, example. The goal of the example is to set the VDS monitor to trip the current greater than 100 amps. According to the MOSFET datasheet, the RDS on value is 1.8 times higher at 175 degrees, which is correct, because when things get hot, they are most often, not always, but most often, increase in resistance. And the maximum RDS on value at VGS at 10 volts is 1.6 milliohms. From these values, the approximate worst case value, sure, that makes sense. Using equation with this value and worst case monitor, we get this voltage. For the example, the value set as 0.31. Okay, I do believe that I actually kind of set up this. Let's see my setup code. I do believe that this is actually used. I just don't remember exactly when. Let's see. So what do we set up? We set up our driver into three-phase mode. We set up our current limits. Oh no, I don't set it up. And if I don't set it up, what is the default actually? This pass allows for adjustment of the deglitch time for VDS over current monitors. The deglitch time can be set. Okay. That's all. So what other mentions of VDS monitors do we have? Gate driver implement adjust VDS voltage monitor to detect overcurrent and short circuit conditions on external power MOSFET. When the monitor voltage is greater than 3 point, longer than the glitch time, an overcurrent condition is detected and action is taken according to the device mode. Sure. The high side VDS monitor measures the voltage between the V drain and SHX in device with 3 current sense amplifiers. Okay. What? No, okay. If the current sense amplifier isn't used, tie SP pin to the common ground of the external half bridges. Hold on a second. Measures the voltage between the drain and... I think those will actually not be useful for us. And the point they will not be useful for us is because I don't use this. Because my variant of the driver doesn't have external current sensors, because I use inline current sensors because they are the right way to do it. So I believe that 7 out of 10 errors are not errors we can ever get because we don't measure any current by the driver IC itself, which is okay. Not a big deal. So what else do we have in our fault status? Let's get back. Okay, what is gate driver fault? Let's see. Okay, and the gate drive form may be asserted. Okay, the strength of the gate drive current I drive is selected based on the gate drain charge of the external MOSFET. Yes, I do set up in my code as we saw rather, the target rise and fall times at the output if iDrive is selected to be too low for a given MOSFET, then the MOSFET may not turn on completely within the set drive time. And the gate, so the gate drive fault happens when our timing, when transistor is not open in time. This is actually very useful. Let's actually note it, because this is 6 errors at the same time, right? I think I need to open the document twice. Can I open the document twice on Windows? Question mark? Question mark? No, I don't think I can. Let's then open the datasheet on the TI website so that we can read multiple versions. So it will be DRV, this. I don't need your was. Just open me the website. Hello. Okay, this is it. Datasheet. So let's see. Fault status in 2 different words, of course. Status. Here we are. Hold on a second. Oh, wait a minute. There are 2 of them. Was? Oh, there are 2 of them. But why are they called the same? What? It's called VGS status here. What the hell? Oh, so we have way more errors than I thought we had. That makes 0 sense, actually. Let me open my Git and let's see what we actually deleted, what we removed. Uno momento, signore. Oh, where should it be? It should be in dependencies, of course. Here, not here. So let's see. What we removed is a read to the status register and then read to... No, it is a read to the same register, right? The name is... Oh, no. Yes. What? So it was the read to the same register then. But the checks were different. Fault status register, and this is fault status register. I'm confused. What is the address of this register then? 0.01. Fault register 0, fault register 1. Okay, this is confusing as hell, but let's think that is fine, that this is correct. And let's handle if this is correct. So we have quite a few more errors to go through, which is fine, which is absolutely fine. So let's just do it. But now we cannot return 2 values from a C function. So we need a different mechanism to return the registers. And for that, we might as well use 2 functions, because why not, right? And therefore, we'll need to rename the function. So let's go here. So this function will be renamed. It will not be a handle and fault interrupt. It will be rather read fault status 1 rec. And we'll have the same for the second one. And they both will return their values. So let's go and implement them. This will need to change change the description of stream, because changing the description on stream is boring as hell. and here. So let's add our implementations. This will be the first one. And here, let's see what we have here. 0.00. And so we have a proper register. I just had an error then before. Happens to the best of us, I guess. And here we read from the second one. And this, let's call it fault status 2, just to clarify the function. Unless it returns value, so perfect. And then we need to store, this should be removed. Of course, let's make sure it builds. It will not, because in the main we still have a call to a node function, which is fine. But now we need to update this to have two different values. So it will be 16t, the same name, but will be false 2, and this will be false 1. Very nice. And this will be false 1. And at the same time, we need to errors 2 equals to a wrong function name. DRV, nope. UAU, XS, like this, and remove that and this is fine, and the same here. But with correct register, so let's see, this should build, and the follow-up will not. Easy fix, easy fix. So this will happen at some point then. Also, do I need to enable errors somehow? Do I need to allow unfold to work? Or is it working all the time? But we will check it later. So disable driver will happen here because we will have a lot of code below it. So in case of all errors, disable the motor. To do after, one moment, reading the data sheet, some errors may have solutions that will not require the driver disable, question mark. Okay, so let's put this code back, and for that I will actually copy the code we deleted. We will just need to do a bit of magic on it. So in case this is not 0 and this is 2 this time, of course, so is this bit correct? Let's see. Status 2, so it's LC, HC, LB. Sure. So let's just paste it all the way. Not pretty, but it will work as it's supposed to. And we also need to log all the errors, which we will also add shortly. Because logging errors is very useful for embedded system, especially when you can, well, like when you have an ability to download this log when the system is actively running, which we do with our debug interface, debug protocol, which we will improve in half an hour roughly, I'd say. We'll start improving. So let's see. I think we are using a wrong orientation. Too many brackets. Quite a bit too many. Was. No. And no, it's broken. It's fully broken. No. No. That's annoying. I know that I can just run my Clank, but This is just fast. Fast enough. Okay, good. Nice. Very nice. Let's see. Now we need to log all the errors, and let's just continue our numbering system, because these registers also have 10 errors, so it might as well just be absolutely the same. Numbering system. Just continuing. And we will eventually need to do proper error codes here. And this eventually will actually come quite soon, because we are very close to finishing the project to be in a very usable state for other projects that require motors. So debug will be one of the big things we will implement, because when we will use our driver in not air condition, but in not air, but in lab conditions, when like everything is predetermined, but in actual real conditions, we will start having issues, and these issues will require quite a deep debugging to be solved. So debug protocol will be essential, and logging errors is one part of the proper debug protocol. Okay. Now, what do we have now? Now we have all the errors logged, and let's keep reading our datasheet, which says what exactly? It says indicates overcurrent on phase A. So these are not my case, because I just don't have these current sensors. Over temperature warning, sure. This is useful, but this is warning. So this is the case when we don't have to break the motor completely. This is one of the cases. So let's note it, but don't do anything about it for now. And the case is OTW, which is where? Here. So this is the case when the motor can still work, but the power output has to be limited. Okay, so next, let's continue reading our documentation. Indicates pump under voltage fault condition. This is important, sure. And dry faults we just read. All 6 dry faults mean that the transistor gate is not opened in time because its capacitance is too high. So this is what is meant. And all of those are critical, and they can be solved by design. So it's actually kind of nice to have this error enabled when you just try to connect new motor and to test if all your settings are properly set for this motor. So, and no, these are not the motor settings. These are transistor settings. So, and this means that they will never trigger unless I made a mistake in the design or change the transistors. So these errors for me should never trigger because I just properly calculated the values. And unless I didn't, they will trigger, but this will be a one-time fix. Okay, so none of them then will be critical, but this one, or this one, and this one will probably indicate that there is a mechanical damage on the PCB. So what else? Okay. Over temperature shutdown, I would imagine it's over this one. So first we have a warning, and we can still run. And at some point, the warning turns into an error. Sure. And the device just shut down. Under voltage lockout, we discussed. Indicates gate drive fault condition. Sure. Sure, this will never happen for us, I would imagine. And this just holds errors. And there are 11 errors. Okay. So we cannot do much about many of them. So the actual only one we should handle in software somehow is this one. But we will not do this handling today. Having them implemented just as errors we log is already very useful. So we will leave it like this, and we will consider the task done for now. So that we have just debug output. And like if something bad happens, we have a way to monitor this. And then let's actually note that we done the first task for today. And now the fun parts begin. So now we will go and look into my debug protocol. And the idea behind this is very nice, actually. It's great. I'm happy that I implemented this protocol and it works very well, but it has a big issue, which is an architectural one, not a functional one, not a hardware one. It's just an architectural one. So what this protocol does, this whole file, it allows using UART to log values from the microcontroller. And what I mean, we have 3 ways of logging now. If I remember correctly, first one is that I have an error log, as we were just adding errors to the log. So it's just an array that stores errors. And we can save this error log from the device via UART. We can just say at any point in the running system without debugger connected, but with USB UART connected, we can say save us an error log because we would like to see an error log without debugger connected. And why it is useful? Because we can launch or debug or flash rather production software that has all the debug disabled and stuff, but we still are able to debug if we need. And such a debug is important at any point in the device life, even after it being fully put into production, because who knows, maybe there are errors when, like I literally had an issue in practice when the motor encoder connector just got broken out of the PCB. And I managed to, and I was in a different country. It happened in Germany, and I was in a different country. And the person just said, like, here is a log. Your software is shit. It doesn't work. And I looked at the software. I looked at the log errors, and I managed to tell the person that they literally have some issues with encoder connection in 20 minutes. And in 20 minutes, the person just apologized to me because they literally broke off the connector. So this system can be very powerful. So this is the first one. The second system of the debug protocol is to be able to save buffers. And the buffer, in like my definition for the debug protocol, is just an array of values of a particular type. For example, floats or ints or whatever. So we can decide, or rather define, an array, for example, of 400 values. And at some point in the software, in the like running time of the device, it doesn't matter. It may be 20 seconds after the start. It might be 5 days after the start, maybe 3 months. Who knows? Some condition can happen, and this condition will cause our device to store our values into the array. And then this buffer, this array buffer, can be downloaded from the device. And we can see, for example, if particular type of fault happened and the buffer was registered in like quotes, then we can save it and see what happens. And it's essentially especially useful for control systems when you don't want to save like a trigger yes or no, but you want to store a waveform. For example, you had some awful overcurrent condition and you would like to see like what was the current around this point, 400 points plus minus. So we have touch mode in our debug protocol, and the other mode, the last one, is a streaming mode. So we can stream values infinitely, and the limit for this mode is actually the USART bandwidth. So USART is but it is somewhat slow compared to some protocols, but it's kind of faster than many, unless you use like 960 Arduino speeds, baud rates. So if we use high UART speeds, we can actually have like 5,000 points per second of particular value stored into the file. And this is very useful also for control systems, especially when you cannot stop the control system mid something, like you cannot use a stop point, breakpoint. You just log values. You can log them for a second, for 10 seconds, for like 20 minutes, given that this is a stream, like we are limited by the saving ability of our hard drive, how much space we have. And we can have like big files that will store lots of values that we can analyze afterwards. And for control systems, you always analyze waveforms. You do not analyze states. Unless you have to analyze states specifically, but this is a very specific thing to do. And this can also be analyzed using buffers or error log or streams. So this is a general description. But what is the problem with current implementation of the debug protocol? So current implementation sucks in two ways. First way, that it only works with UART. And the second way is that it's integrated into UART. So right now, I cannot, like, the good design for such a useful tool would be to separate it from the medium that it should travel on, so that it should send data on. And currently, in my implementations that I did like half a year ago or so, maybe even longer than half a year, it was highly integrated in UART because it was just quite a fast thing to do, because I believe I implemented the protocol like in 2 or 3 days. But now that I'm older and wiser, I think it's moments, like the moment has come. And in this moment, we need to separate our UART and our debug protocol to be two separate things, so that we can connect them and use them together, but separately. So these are the tasks for today. First, I need to remember how it works completely, because it's quite a lot of code. And then after I've done reading this, which should be relatively fast, reading and explaining, if anyone will have questions, we will start thinking about how we separate them, and then we will separate them. And if we manage to separate them today, it will be a huge success, because it's not an easiest one to work with. But I hope we will do decent progress today. And we will start after a short break for me. One moment. Okay. Brothers, sisters, and viewbots, let's start working. And let's start learning what the hell was my protocol about. So 300 lines in the C file. Oh, it doesn't look that bad actually, so we might as well do it quickly. Let's start with our H file. So queue length, or actually, while talking on my phone with my father, I remembered one more issue of this implementation, and that it kinda blocks, not kinda, but fully blocks the UART. So UART that is used by this protocol can be used by only this protocol. And the improvement I would like to introduce is to be able to use this protocol with other communications in the same interface. So I would like to send custom non-debug protocol related messages also in both directions. This will be a very nice optimization for one of the projects that will come very soon. I have nice plans for those who may tune in a few streams, may see an interesting surprise. Just saying, just saying. But first, this is probably the biggest blocker right now of my idea, so we need to clean it up properly. So, yes, this number is fine and understandable. It's just a number, like the queue length of the UART messages we may send to the device. Then we have our codes, establish connection, close connection, keep alive. Okay, read error log. This is what I described. We can just send an error log to our device to save it into a CSV file. Read buffers, the same thing, to save our buffers that we predefined into the CSV file here. Streaming has multiple calls because we can start it, or we can send a message, and we can also stop it. Nice. And also we have a generic request, and generic request, there are 16 of them, and they allow you to call a callback, and the callbacks are weak. So they are defined as weak, so the user can easily just change them in whatever they want. So you can implement with this protocol like 16 unique messages just that are 1 or 0, and just do something without parameters. So, saying that, what functions do we have here? We have only 4 functions, actually. It's setup interface. This function should go. Must not be here. Most likely, probably breaks hardware where in the dependence of the implementation. Okay. Queue message, update message queue, and handle RX. Perfect. This actually looks kind of manageable. Let's see what we have in our C file. So tx request. We have message pointer and the length of the message pointer. Sure. And we have array of those probably somewhere. Right? Yes, here. And this is txq. So we have requests that we need to send, write index, read index, active queue size, which is an amount of messages we haven't sent yet. And tx is busy if we are currently sending a message. Perfect. So that looks rather easy so far. I hope you can follow along. Everyone who is watching. So, static variables, what do they do? Debug connection is established. Not sure this functionality is needed is a good question. I'm not sure either. Past me, I'm not sure either. So predefined answers for different possible debug interface requests. Very nice. very, very nice. So let's see, we have an acknowledgement message. It can be easily const. Or rather, let's not, let's do it. Maybe something will break. Let's see. If I build it, will it break? Oh, it will not break, but it will. Yes, it will complain that it has to remove the const qualifier. So let's not make it const. This is fine like this. So message error log properties. So we acknowledge the message. And the message acknowledgement is 2 bytes. Then we acknowledge the message code. And then we have the answer prepared. Sure. Message buffer properties. Sure, same deal. Buffer description. What is that? I don't remember. We will see. And then message stream properties has quite a few bits to fill. Oh, they actually are explained. So the first is number of buffers we have installed and size of buffers. And all buffers have the same size, of course, in our implementation. So this makes sense. And each buffer then will have this. Oh, and each buffer then will require our master to send an explainer request. Sure. Sure. And our stream has an ID, number of fields that can be maximum of 255 entries per message. This is a way for stream to either be able to send messages, one message at a time with fixed interval, for example, 100 milliseconds, or for example, to stack 4 messages together and send them every 400 milliseconds. And both have use cases, so this is allowed. U32 stream timeout. Sure, if stream doesn't send values in particular duration, it is considered to be timed out. And bytes per message. And this also makes sense. Sure. And stream, message start. Sure. Okay. So set up debug interface. Set up debug interface, and this is hardware dependent code, which is unfortunate. We need to start moving this. And where will we move it? We will move it here. And we have a UART here. So let's say we will define a new file, and let's call it debug protocol. Debug. Let's say UART debug protocol beef. Let's do a pragma once. And let's also create a C version of this file. And let's copy name for the ease of use. So let's create a C version because we will need it. And the C version has to include our H version, of course. .h. Looks very nice. And let's move our peripheral setups here because we don't want our peripheral setups to be in the debug protocol itself. The debug protocol should be independent on the hardware. Even if it uses UART, it's possible to do it this way. Okay. So we can quite literally, I would imagine, just do this. And we also can probably split the screen, move it a bit here. And UART baud rate is a definition that should be included in here. So include device definitions. Sure. What else? Do we need something else? We do, because this is a hardware file, of course. It needs device includes. So it needs to know what MCU it works with. And this function has to be defined here to be able for us to call it from outside. Okay. UART, PF definitions, 500 for UART is a nice frequency, good enough. It's supported by almost everything, which is fine. Now, let's go back to our debug protocol and let's start undressing it as much as we can. So we need to clean each file from this. It is not any longer existed here, but also we have static files.
Dialisk is now following.
Hello, Angelisk. Thank you so much for the follow. Hope you're enjoying the stream. If you have any questions, feel free to ask. I appreciate the follow a lot. So let's go and find our static variables. Well, not variables, but static functions. Actually, where the hell are they? Oh, they are here in debug.pf. So it already exists. It already exists. But what is different then? We have our GPIOs. So we just call this function, and then we also call the setup UART DMA interrupt. Is it correct way to do it? Oh, so these are already implemented. This is just how we should call it in our main then. Okay, okay, so this, we don't need these files. Sure, and this actually raises even more questions. Why do we have it implemented inside the protocol itself in the first place? But let's go to our main, which is quite huge. We will move it into functions, separate functions at some point. Let's put these calls here. Enable UART debug protocol. And let's comment them out. And these two files will go to the bin then. We don't need them. Okay, so we moved out our implementation part, and let's now but rather change our communication part. So how do we do this? We do this by going to our protocol.c and start reading this, because we need to understand what the hell is even going on. So what is the issue here? It expects this, but gets const at some point. At what point? At no point, because we changed this. Sure. And if we change this, this is completely fine. One moment. One moment. I am back. So, queue message, the most important part, and the part that can actually make sure that our protocol is not only for debug. So it send message to the UART is queue is empty, or send it to the queue if we already in transition of values. Okay. So in this case, we do what? We just check the function. So I think this was debugged by me quite a few times, and I had an error here, but now it should work absolutely fine. But this part, we need to do this part has to be called by a function pointer rather than directly. This is incredibly important because this will allow us to actually make this implementation hardware independent. Because right now it calls a UART implementation directly. Okay, so we will do it. We noted this first note. Nothing else in this function in any way, shape, or form is dependent on the hardware. Okay, let's see other functions. Update message queue. This is what we call after our UART interrupt calls, and the UART interrupt is called after we receive the reply. Because in this protocol particularly, we expect the master to reply to every single message. Oh, no, it's not. It rather is called after we finish sending the message, right? Let's actually read the comments. So send next message if available from the queue, reset communication if no message is available, must be called in the TX DMA. Yes, so it's transfer DMA. So we send the message, and after we finish sending our message, this is called. So we actually do not expect answers to anything other than initial setup. I lied to you. I'm sorry. Okay, so let's read it. Yes, these are very important IRQ disables because this function is supposed to be interrupt, how is it called? Safe, thread safe. So that interruption at any point here, for example, if we remove this part, like all of them, what can happen is that at this point, we already thought the queue is empty, and we disable at this point interrupt interrupt is called that sends a UART message, but the flag is already checked, so it will set RTX busy to 0, and it will disable a protocol. So in this very, very, very uncommon, like very unlikely scenario, the debug protocol will die unless we do this, which is disable interrupts by a very short amount of time, so that we can safely remove this, so that in case our message needs to be scheduled right after this, it will restart the message process here. So this is explained. Busy, enable IRQs again, of course, and if we still have messages to send, we just update the indexes, send the message. This is also a hardware dependent moment, so to do will be the same. This is absolutely a single function that will have an absolutely similar solution to this. Okay, and we just update the queue size. Very easy function to understand. So let's go next. Handles all debug interface RIX requests. So this is where all our main logic implemented. Okay, so this is probably the last function. Those are our callbacks, and we have two more. This is a short one, and this is a big boy. Big boy. Let's read it. Let's remember how our debug protocol works in the first place before we can improve it. So what to-dos I have from myself from half a year ago. Write the documentation for the protocol. It's important because protocol is a bit complicated. Sure, it is need to be done, but not now. This implementation doesn't support options to handle requests not as part of the debug protocol. Yes, and we can solve it today. So this we will solve today, I'm sure. Solvable today. Okay, so let's start reading what we have right now. So our handle RIX takes a message that we received as a reply and also the message length. Very easy. So if message length is less than 2, we expect that this is not part of the debug protocol and we fail gracefully. Now, actually, I think I would like to start implementing the independence of the protocol right away. So let's add function. So debug interface. And what will we do? Check message. No, what will be the correct name? So this function should return 1 or like anything that will be treated in the if statement as 1 if the message is considered a part of the debug protocol. So how will we name it? Debug ITF. I don't want to use too many words. Function naming is hard. The hardest part of the programming is figuring out how to call your functions. Okay. So, is there a smart word to use? Check message prefix question mark. Okay, whatever. I will add to do rename. This is a very common thing we do on this stream, is that we just come up with whatever name we come up with and then we rename it later. Okay, so what will it take? It will take this value. This will take absolutely the same values, and this function will actually have a return value. And the return value, let's say it will be 32 int, because why not? It doesn't matter what you use as Boolean in C. It actually doesn't matter in any language almost. It's always an int type that is biggest for your, not biggest, but optimal for your system, most likely, most often. Okay. So let's implement it. And the implementation will be very simple, but let's implement it in a particular place, which is here. Is this function, this function is part of the debug utils, but it is stored in the debug protocol. What? Oh, it exists in. Oh, hold on a second. It is a weak function. Okay, this makes sense. We will read it later. So it has to make sense then, but here I have to add a comment. To do add an explainer comment. It's important. Oh, and debug utils is also what we need to read, because this is actually where the juice happens. So debug utils are incredibly important. So let's actually start reading debug utils first before we start working with the protocol. It's more important even than the protocol itself. Oof. So a little bit more work, but we can do this. And our debug utils are stored in the generic utils because they are hardware independent and can be used in any device, anywhere. So what do we have in our H file? This is not very independent. These are GCC flags. So I would consider moving all of those actually to do. Those are not device in the those independent in general, independent. They are GCC specific. So they must be moved into a different place. For example, we have a nice place for this is in 2 ARM Cortex M utils. So these are movable, but this is not. This should stay here. So they are separate. So this is separate. Like this. So this is our log error implementation. So if we enable, or rather, if we not disable it, we log error into an array. And if we disable logging, all these functions can stay in the code, but they will do effectively nothing. Okay. And we also have an assert error, which I do not use much. Oh, so it's kind of interesting. So it only saves to the log error if error happens, which is kind of nice, actually. So this can be used instead of if error then something. Actually, I should start using this more because this is useful. Why am I not using this more? So let's also see what we have here. Is we have a define rather include, but only if this include is available. Very useful, actually. It's very useful, actually. Okay. So let's continue. This is fine. And let's see what we have here. We have our error log, which for now, for current implementation, is just an array of values, but it can be bigger. For example, error log can store some error information. It can store a point in memory of the microcontroller. It can store a timestamp of the error. So there are different ways to handle this, but currently we use the most basic, simplest way of them all is just storing the code itself. Okay. So we have many buffers, and buffers are very simple. They are just an array of values, and the pointer to the value we can write next, and the pointer to the value. No, this is it. And we also have a delay access count, and this is a very specific value. And the point of this value was that in case we would like to, for example, we have a function that calls a save every 1 millisecond. And we would like to say that we would like to start saving after 200 calls. And this is where this value comes up. So if we put 200 here, so the first 200 calls to the function that writes to these structs are skipped, and the actual writing starts after 200. So this is implemented into the struct itself just because it was very often use case in our case. So we have debug buffers for most of the types commonly used. On microcontrollers, I don't see, no, I do see, yes, all of them. We have an enumerator to decide what type of array we work with, not array, but buffer. And this is custom made. It is not a standard at any point in any way. So, and we have also buffer storage. So we can create multiple buffers, and for a protocol to save them into the PC to work, we need an organized way for them to be stored together. So then we have a buffer limit count. So we cannot create more than 32 buffers, and the value is rather arbitrary. And each buffer is 64 fields. Is the right name? I'm sorry. Fields or entrances or whatever you want to call it. Let's see. And what we have a write index, and I don't remember what a read request count is. So to do explain. I don't remember what it does. Oh my god, explain. So we have another struct, and what is this to do? Update the struct comments with proper init semantic we were using somewhere else. I have no idea what it means. I was probably not in the sharpest of mind when I wrote it. But let's see. Example, we would like to send 5 points, x and y stored as f32. Therefore, our entry will be, so this, what is this? This is a com stream. So this is how we set up a streaming, and our entries will be f32, f32. So we would like to send tuples of floats. Every message will have 5 entries to not send messages too often, or because we have 5 different points we want to send at a time. Sure. In this situation, all 5 points will be defaultly saved as 5 separate lines in the log.csv. Sure, this makes sense in this particular case. In this case, our message will have a message byte size of 2.4.5. 4 is the size of the float. 2 is 2 messages per entry, and 5 entries per message per debug message. Meaning the size of 10 floats, as we will not have any alignment issues. Sure. Entries per message count equals to 5. Entry fields equals type this, and entry fields count equals 2. So this explains how to set this. Okay, this is actually a very good example on how to use it. In this example, it is possible to also create a single 10 float entry like this, but by default, it will be set as a single line in the CSV file. So yes, we have different approaches on how to do it properly, depending on what you want to achieve with your life. The appropriate approach should be selected based on the goal. Perfect. So we will store an array to the message that we will need to create in advance. Sure. Timeout, message byte size. Okay. Entries per message count. Okay, it's also explained. This is how many lines will be in CSV file. ID is an arbitrary number that you would like to use for documentation purposes, organization purposes. Entry field counts is sure. Per message entry, sure. Is active and entry field types. And we can have maximum of 32 fields in a stream message. Sure, stream entry. Okay, so these are all the structures we need. This makes total sense. And actually, this can come as a good example of comparison of C and C++, because if in C++, this can be defined as a template, because all of them are literally the same with a single difference of this array. But here come another side of the comparison. If this was implemented this way, then the issue would be that we will have very low visibility and readability and understanding of what is going on. And in C, we have to implement like many functions that are very similar, but they are tightly controlled, which is nice. Now, let's see what functions do we support in our debug protocol. And this is just an example of what we need to add to our definitions file if we want to enable different values here. Sure, and this is error checking. Okay, sure. Sure. And what is this? Okay. This error assumes that we know that debug utils can be used with UART, and UART limits our ability to send the data out, which is not perfect, but also will probably work for most of the protocols. But I would imagine that I'm not sure, but I would imagine that this is not the best place for this error check, as it assumes the interface we use to work with the debug utils in advance. Maybe should be moved into a specific location of a USART implementation. I will think about it later, not for the stream. So let's see our functions. We have debug shutdown system. And this is a weak function that we can call in case something critical happens. And I actually need to use this function more because I believe this is a very important one. And we actually need to use it more in our motor control. So let's actually go to our motor control and let's add a to-do for ourselves to use this function more. Debugging. So use, implement, and use was no utils. This function more. In the code. And this looks absolutely awful. Sure. I don't think any of it is needed. La 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 la. Nor do I think this is needed actually. What the hell is that even? Oh my god. Oh my god. Okay, so note it for ourselves. Now, this function is clear how to use. Let's go next. Log error. And log error is currently very simple because we only store errors as uint16. So we don't have much to do with them. We just check if error is 0 and we return, because if error is 0, it is not an error in our implementation. Then we just increment the count and put the error into the error log. We skip right into the log if the log is full. This is a limitation currently. There are like 2 ways to handle this. One way is to overwrite all the errors in case you would like to actually. Let's add to do. Let's add to do. Implement a switch to change between overflow and overwrite behavior of the error log for situations when we want to overwrite old errors with new ones to save newest errors to when reading using the debug protocol. So there are 2 ways to do it. First is if you want only the first errors, and this helps you to usually debug setup issues on early stages of the development. And the second one is when you have your device in the field most often, and you want to see what were the latest errors, for example, when device was running for like 7 days or something. Okay. So let's see. So to do implement overwrite option. And we just, otherwise we save our error to the position, increment the position, and return the error itself. So that log error returning the error it logs. Very easy, but the location for this is kind of incorrect. It's just complete mess for now, but whatever. And this function just returns a pointer to the error log because we only have one error log that is statically hidden in the C file. Because we don't want to accidentally create multiple of them, and we only work with a single one. And this we need to return so that the debug protocol can store this can send this to the master. And therefore, to send it, it needs to be converted into a message. And therefore, we need to know the pointer to this type, to this address. Very easy. Let's continue reading. So these are work with buffers, and buffers are very easy. There are like 12 functions. They are all implemented the same. We just put the value into the buffer by seeing if, first of all, as I explained before, if delay is higher than 0, we skip the write and decrement the delay until it's 0. And after it's 0, we put the values into the buffer until buffer is full. And we can also reset the buffer, and resetting the buffer is very easy. Oh, I think the buffer reset should take one more argument, actually. Actually thinking about it now, I would imagine that the buffer reset should take new delay as an input, and this will be a correct behavior. So let's actually do this. And how do we store it? We store it as a uint16. And let's implement it for all the variants is new delay. And let's add it to all the functions. Oof. Okay, so here, 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 here. Yes, and now let's go and start implementing them. Oof. Misclick. So this will be as target buffer delay access count equals new delay. Very nice. And we don't need any checks in here because uint value cannot be negative, and we have absolutely no issue with the value being absolute maximum, which is 65,000. Like if the user decide this, oh, this is an accident, like it still will work, just longer. Just will take longer. So let's keep going. Let's make sure that everything is styled properly, because styling is important in my books. Let's add our argument here, and this will actually be absolutely the same. It will be target buffer, new delay, ready. So we keep going. This is all the same. Here we add an argument and we do target buffer, this new delay, this boom, bam, boom, dump dumps, add argument, save argument, like this. Keep going. Keep going. Sure, add argument, save argument, like this. Sure, and now we are why is this different? I didn't like this, that I have many exactly same functions with different types, so I'm not sure if this can be handled differently. But if it's possible, something to do later. Let's actually think about this to do right now. Can we do anything about it? Now that I'm older and smarter, do I have any solutions to this issue? Because all of them seems like they do absolutely the same thing, but C doesn't support this behavior directly. So what all are our options? So the buffer is an array of values. What we can do is, instead of making this an array of ints, we can make it an array of void pointers. Was hold on a second. But to write the value into the array, you need to know the size of the value. Otherwise, you will mess up everything. So otherwise, you will mess up everything. So you have to know the value in some place. You have to know that this array is an array of like ints or floats or whatever. Do we have a good solution to this issue? Do we or don't we? I actually don't think we do. And I actually don't think that this issue needs a solution, which is the biggest deal. Like, I'm not sure that I need to solve it, actually. I'm not entirely sure. Actually, I actually don't think I don't need to solve it. I would rather just remove this. Yes, I don't like it much, but alternatives, which is C++ templates or something, are even worse. I rather have it like this. Like I rather will. So after a short existential crisis, but hold on a second. What we can do is we can actually make this function a single one. And how we can make this is by doing this. Oh, this will be a smart solution of sorts. And why it is smart? Because this part is always the same for every single one of them. And therefore, actually, to make it even simpler, we can because yes, you know what? Let's do it. Let's do it because we will remove quite a few functions with the cost of nothing. Type def struct. It will be debug buffers buffer. Not unique. What is the opposite of being unique? Is being common. Common fields. The name is too long. Again, I'm famous for having names that are too long. And this will have this. And because it will have it, and it will have it at the first instance, we can always... Actually, I don't think this helps anything. Like my thinking right now is that I can... Like what I was giving, what I was thinking is that I can use a void pointer in the function and provide any buffer as a void pointer. And my thinking was that by creating this field, I can make a separate function that can provide only the field of this struct. For example, if we here add fields like this and remove those, we can add like this buffer dot these fields to the function. But this is kind of confusing because we're calling the function reset the buffer, and technically it is reset the buffer because we don't remove any values that was stored. We just reset the right index to 0. This is confusing for user, right? It will be very confusing for user, I would imagine. Or is it? Or is it? Like if we use a void pointer solution, this gives us nothing. We might as well just leave it like this. And if we use the implementation when we send these fields, then it becomes kind of confusing to read. Or is it? No, I actually like this approach more. This will break a lot of things, but it's worth it. Buffer, maybe we can call it just buffer common fields. Can I also make it static so that other files don't see it? Static. So I don't want any other file to be able to use this struct for themselves. Oh, I cannot do it. Okay. Okay. Not today. Oh, no. Hold on a second. Maybe I can do this. I just changed the name. Static buffers common fields. Will this work? multiple storage classes in declaration specific class. Type def static struct. Can struct be static? I don't think it can. Okay. Okay, I take it. I take this back. Sure. Sure. I take this back. But anyways, we go and we change this everywhere. And we can remove quite a few of the functions we have. Not all of them, but a lot of them. But quite a lot of them. Anything else? No. Now we will have a lot of code breaking. Oh. Let's close quite a few projects to have less errors, because we would like to work with them only in the single project. 44. It is expected because we have multiple implementations, but now what we can do is we can delete, and this will be debug reset buffer, and the reset will be buffer common fields pointer, of course, target buffer fields, and this will be implemented here like target buffer fields rather fields fields. My god. And this will be next write index equals 0 and target buffer fields while delay new delay. Okay, and this will go to hell. 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 And that's about it. And we need to fix like 7 functions. It should be easy enough. Should be easy enough. Because we just need to provide fields everywhere. Everywhere. Like this. This function is fixed, right? Right? Was? It is not fixed. Hello? Target buffer dot fields dot write delay access count. So it is correct then. Why are you not happy? Invalid type argument of have buffer common fields. What? Let rebuild the index. Maybe it is an index issue. So it should be fixed now. What the hell? I'm confused. Let's comment out all other broken functions and let's deal with this one at a time. Let's deal with this one at a time. So we go here and we check. This type def struct is correct, is implemented correctly, and it is used correctly, right? It does. Okay. So what the hell is this error then? What is going on? So let's try target buffer fields dot base field stop, and let's say whatever you int 16 t, oh my god, t test equals to this. And let's build it. And this is an unused variable, but it works. Oh, because it is not a pointer. I see. I am a dumbass. Of course. Because this is a pointer, but this field is not a pointer. Sure. Sure. I'm just stupid. Just stupid. Somewhat. Now it will be fixed. Okay, okay. Oh, hold on a second. Now it makes so much sense. Of course, of course. Of course it does. And now let's start fixing everything. This function is fixed. This function is fixed almost. Should be fixed now. Very nice. Very, very nice. Fix this and this. This function should be fixed. And this function should be fixed. And the last one. Oh no, I made a mistake. I fixed the mistake. So here and here and here. So perfect. Now we cleaned quite a few. Okay. Oh my god. Brother. Hey, brother. Do you still believe in love? I wonder. Oh. The skies kept turning down for you. There is nothing in this world I wouldn't do. Oh. And if I'm far from home. Okay. Brother, I will hear you call. Now, we changed those. And let's keep reading. So, debug register com buffer. Registering the buffer does what? We register it to the buffer storage. And we would like to register them to the buffer storage in case we would like to transfer them. To prepare them for transfer. So if we registered too many buffers, we return. We also need to log an error, which will be too many buffers are already registered to do at a proper error code. Okay. So next, if buffer pointer is 0, this is also an error, a loggable error, which should say, let's say this, user provided null pointer. Okay. This is also a loggable error. 6. And the error is explained here. Unknown buffer type. Very nice. And what happens here? If everything is correct, we just write the pointer to the buffer type. We save buffer type in the array, and we say the pointer to the buffer type, which is a void pointer, I would imagine. This is an array of void pointers, correct? To the buffer. Actually, now thinking about it, let me think for a moment longer. Let me think for a moment longer. Just for a moment. No. I was thinking about if we can use the buffer types to remove these functions and to make one function. And we technically can, but this function will be huge and will be performance inducing, and this will be annoying. So let's not do this. So registration of the buffer is easy and understandable. Debug unregister all common buffers. Very easy as well. We just set our write index to the 0. And even though we have values written to the array, they are not actionable because pointer, rather index, is 0. Okay. So debug get com buffers. So we need to get a pointer to our buffers, and our buffers are debug com buffers, and this is our storage for our buffers. So we have only one of those. Sure, makes sense to me. What else do we have? Register com stream. So this is a loggable error and it is logged, and it's also returned at this point. Sure. And this, I don't know. I'm not sure if I should return this error. This is a question. This is an actually architectural question to do. A big architectural question. Should I return error codes from functions if I log errors inside of them? And if yes, always or in defined particular cases? Question mark, question mark. Okay. So if we register com stream, overwrite an already registered stream. So currently our implementation supports only one stream being registered because we support only one protocol, which is more than correct, and having two registers for this protocol is excessive. And if you need this functionality, you probably need to do some custom thing. So we will keep it like this. And let's see. Let's keep cleaning our code. So if we didn't provide null pointer and we don't have a buffer registered, we register the buffer. Very easy. So unregister com stream is very easy as well. We just set our active stream pointer to 0 after setting it active to 0 as well. Sure, makes sense. And debug get active com stream is when we need to send it over the debug protocol. And what is this function? Why is this function needed? So let's see if we have anything in the H file to give us any clues. So debug com stream, that's a very nice to do. I would very actively want to know it because it's explained nothing. So sense current state of the message stored in active com stream if stream is registered and open. Sense current state. I think it has to be. It's supposed to send. It doesn't send it because it does nothing. To do update explainer. This function must be implemented in the file responsible for the debugging interface handling. Sure. But it will be not debug interface, but debug. No, it's debug. Yes, it's debug interface because interface is a hardware medium we use to transfer, which is like UART. And protocol is like if message is X, then we reply Y. This is protocol. So sends current state of the message stored. Okay, we have an example of how it's done there in the UART debug protocol. So we can use this example. And let's keep going. So we've read this file. It is kind of clean and easy to understand, especially after we cleaned up a bit of repeating functions, removing a lot of repeating code. We added a few to-dos, which we will not handle today. Today we just have to, not have to, but we should try to our best to separate the UART implementation from the debug protocol itself. Now we can finally go back to our debug protocol and continue reading because we have one more function to go, but I need a 2-minute break. Be right back. I'm back. Let's continue. Let's finish reading our debug protocol. So, I remember we were planning to implement a function before I suddenly got distracted. We were planning to implement the function that would check this, if this message is a part of the debug protocol. And now thinking about it, do I need this? Really? Do I actually need this? I don't think I do. I don't think this is necessary. So actually, let's not do it for now. Because I know what I would like to achieve and I know how. I just think it's hard to explain my problems. So let's see, let's keep going. If message is shorter than 2 bytes, it is an error because all messages should start with 0xAAOX55 in hex. And if it is not the case, we haven't received what we were supposed to receive. Then, if the message first and second point, or like first is not AA and second is not 55, this is also not a part of our debug protocol, so we also send a NUC. Sure. Now, if the message length is 3, we have a few options that expect only 3 as message lengths, so let's handle them. But before we do it, let's see how our debug update com stream is implemented in this version. So debug com stream, active stream, debug get active stream. Sure, this is an independent function, so that it is not important. If active stream is null, we just do nothing because no stream is registered. Sure, and this is not an error. If active stream is not active, I'd say it's activated stream is not active then. Activated stream, let's call it like this, it will be better to read. So we just do nothing because we cannot update anything. And in case we can update anything, we need to debug ITF-Q message. And want then. Oh, we queue 2 messages in a row because we need to send that we are sending a message, and then we need to send the message itself. This is how protocol works. And now looking at this, nothing here is in any particular way UART dependent or hardware dependent. So we might as well use it as a general implementation, actually. Or can we? Or can we is a question. Because if this is a part of the debug protocol, also, if debug protocol is a universal thing, or if it will become a universal thing, what does it have? Can we actually put debug protocol inside the debug utils then? If this will become a universal thing. Let's see. This can be quite an optimization, actually. Quite a nice one. So can we actually do this? So debug utils just handle buffers, streams, and all of it. And debug protocol just handles like sending the buffers and everything else, right? Is this correct? I think we have one issue with this idea. The issue is our function that handles our Rx, our receive. The send messages are fine, but the receive messages are awful. Let's think about it. Like, we have time, we can think through this because we develop for the future. I may want to use this debug protocol until I bloody die. My children will use this debug protocol. Let's think this way. So if we would like to make it long term, what would be the best architectural decision for us here? The best one I can come up with right now, with my knowledge level. So what will this be? What will this be? Queuing messages doesn't seem like a problem at all, because queuing messages doesn't depend on anything at all, actually. Right? Just queues messages and sends them somehow. It doesn't even know what messages are, neither it knows what the interface is. Like, it knows nothing. So this function can be moved independently easily. The same for this function. We just need one point of issues to solve this singular point of breakage. But this is a huge single issue, a terrible one. This function can also be moved. But this is awful. And it is awful. Why? Because it is protocol dependent. It must know protocol in advance. It must know all of it. So how do we do this then? I actually think that I believe that I know how to do this. Let me think for 1 more minute. I am pretty sure that in my head I'm very close to the solution. I'm pretty sure I am, but I might be mistaken. This happened quite a few times in my life. I might be very mistaken. Oof, rough. What the hell is this? What I've done? What I've done? Start again. Oh, I see what I've done. Fixed. Okay, thinking. I'm thinking very hard right now. I will need 2 function pointers, I believe. And if I will implement 2 function pointers here, I think with 2 function pointers, all of it, absolutely every single thing here can be universal. If only I will have 2 function pointers. And is having 2 function pointers a problem? Absolutely not. But let me make sure that in my head I only need 2, because if I need more, it may be a problem. Let me think. Okay, I'm breaking a lot of stuff. I'm so glad I use Git here, because if I didn't use Git, I would be in trouble, in so much trouble. But I believe I have a solution. So let's try to implement it. And to implement this solution, we will actually move this to the debug utils, because this can be done as a pure debug util. So let's do it one step at a time. One step at a time. We need to split it. We will use a something somewhere. It will be called debug UART protocol. Like it will be called like this because this is hardware dependent part. So this is hardware dependent part, and this is already not hardware dependent part. So this is hardware dependent part, or rather protocol dependent part, but these are not, and this is. So let's start moving. This goes away. So this will be in debug utils. In debug utilities, where are they? Where are they? Where is the detonator? Yeah. Okay. File configurations. So we don't have a way back. We are committed. We are committed to greatness. We are committed to greatness or suicide. I have not decided yet. So this stays here because this is a part of the UART. This also has to move. All of it? I do believe that all of it, actually. I do believe that all of it will be moved out of here to here. No, not here. Here. And in this case, this function will make sense here. So this will be like that. And this will be debug. So will we call it still debug protocol, or will we call it debug interface? Is definitely wrong. Debug protocol, we can call it debug protocol common, because this is a common part of the debug protocol that we need to build upon of to make the debug protocol work. So let's call it, and I will add my usual to do add in name. This will be debug protocol common functions. So this is common for all implementations of debug protocols. And now we need to go here and implement it correctly. And this will be here. We need to move all of it here. And we need to make a line break here for readability. And I also think I broke something quite terribly. I'm terribly sorry. Like that. And we will also need to create a structure with two function pointers that will be part of a protocol, of a common protocol. And actually this structure will be not a common structure, not. Okay, let me think. It's kind of assembles in my mind. Like I'm getting closer. I'm like creeping up on a solution. Like slowly but surely. We're getting there. So let's see. So we need to save all of it here because this is part of an implementation of a particular interface. What is this to do? This is the version of device debug protocol moved from the M1 project, but we are in the M1 project. It is developed inside purpose. Okay, we are solving this issue right now. So we can remove it because we will solve it soon enough. Now we go here, and what do we need to move? These have to move. They are not longer part of this implementation. They are not important here. They are important here. And here is like this. Local types declarations. Any other declarations, this is already an implementation of a function. And these are global function implementation. Global functions, function implementations. 1, 2, 3. 1, 2, 3. Almost nice. So these are times, these are variables. I will need to add one line break here as well later. Now, do we need to move anything else? Debug connection is established. It is not used any at all for now. These should be here because they are UART related. Here, these functions are properly fully moved to this place. They are not needed here any longer. Very nice, very nice. Have I removed a comment? I have. Let's copy the comment as well, because I believe this is correct. No sense new. Oh, yes. So this will have to go. So this will have to be updated to update. Okay, so let's remove this. We have to move this as well. Queuing the message is part of the protocol in general. Oh, this will work so nicely when we finish. I am sure of it now. I'm very positive that it will be a good implementation. We just need to get there. So we remove it from here, and we also have a single place to update here and update the description, because it also requires, not requires, but it also relies on hardware, which we don't have right now. So let's do update the description. And handle Rx will be different. So this will actually stay here, but it will be called differently. So let's see. I would imagine this is like that. Global functions declarations. This will have a single function, 2 functions, n functions. Let's see. Debug protocol, proto UART handle Rx. This will be a nice name. I like this name. And this will, oh, like this. All right. All of these are needed here. And these can stay. Oh, and all of this can stay because it's now not important any longer. And I also think that this is actually hardware independent mostly. Let's read it. Let's read it. Let's read through this. Queue message is hardware independent, sure, but it is hardware independent, but protocol, not protocol, but interface dependent. It relies on the interface being UART exactly. So debug ITF establish connection code. So this is UART. Establish connection, sure, it will be here, wherever. Okay. So this is also hardware independent, but interface dependent. So this also independent. So it's debug ITF keep alive code. Sure, we just keep the connection alive. Okay. So now read error log. We would like to save error log at this point. So we need to send error log properties that are predefined. Almost predefined. We just need to put this there, that here. Actually, now thinking about it, I can make it even nicer. I can. No, I can't. I can't do it nicer. It will work. I'm just talking to myself at this point. I have thoughts in my mind, but I am just jumping too fast without explaining the previous thought to the next thought. I'm so sorry. Okay. So here we read error log, so we update the error log version, and we also put an error log size, correct? Do we put error log size? Yes, we take the third element as a pointer and we put it here so it works in the pointer conversion way, which is a reliable way if you know how to do it. So we send an error log. This is fine and this is not. And we just send it. So it is also hardware independent actually. So I believe that this whole function is hardware independent but protocol dependent, which is unfortunate, but it is what it is. And until I implement something like CanFD, I will not know how to do it better. And when CanFD will be implemented, we will update this to work nicer. But until then, we have to work with what we have at the moment. So read buffers. When we read buffers, we see if we have any buffers, correct? So yes, we put number of buffers we have. We send it. Now we also send how big the buffers are, sure. And we send this. Oh, this is just an explainer because, okay, the protocol works in a way that the master can ask us how many buffers we have and their properties. And we say, for example, we have 5 buffers registered and they are 400 bytes, not bytes, but elements, entries long. And after that, master can decide to read one of them or all of them in any order. So that's why it's handled in 2 different ways. And now we have our buffers particular read. So we read a particular buffer by the buffer index code, which is fine. So we do all the math. Nothing here relies on hardware still. And I don't think anywhere here will rely on hardware. So actually we moved to this position only functions that are not reliant on hardware. Or rather, the functions that are reliant on hardware. And we kept functions that are not reliant on hardware here, which we were supposed to be doing an opposite way. But it will all make sense in 20 minutes, I promise. I promise that it will all make sense. It will all still work nicely. So let's see if it actually builds even. Oh, of course it will not build. Why am I doing this? Why am I doing this? Actually, this is problematic. This is very problematic because this relies on hardware in 4 places, not in 3 places, in 2 places. Oh, this is actually unfortunate as hell. Hello? What is the problem? Because given that we are trying to be hardware independent, we don't know what it means to disable or enable interrupts because we are not on a hardware level with this function. So we will need to provide 4 function pointers, not 2. So the function pointer to disabling interrupt will have to be provided even though it is a single assembly command. We will still have to provide it if we want to make it hardware independent. And we do want to make it hardware independent, so we will do this. But this is unfortunate because this makes it kinda annoying. Because right now it is a static force in line and we will have to force it to be a proper function call. Oh my god. Oh my god. Let me think for a moment. I don't like this. Like I can live with 2 function pointers that are big functions, but when we have a function that is called relatively often, like every time we need to send the message, and instead of being a one-liner, we have to do a full-blown function call twice instead of 2 lines, it actually makes the function like 20 cycles longer to implement, to execute, and 20 cycles is quite a lot when you call function like 10,000 times per second. So what are our options then? Can we do it better? Do better. Because this file has to be hardware independent. Otherwise, it will not work. On the other hand, I already force people into my style by having this here. So I might as well. Fuck. Let me think. I can force to user to provide these functions separately. And if these functions are provided separately, they will still be one-line calls. One-line calls. Should I do this? I'm not sure I like it, but I'm also not sure that I don't like it, because I would imagine that there will not be like 10,000 people who would like to use it, like my hardware abstraction and my debugging tools. And if I would imagine that I develop it mostly for myself, my team, and like 3 lurkers that would like to use my debugging utilities and tools for their own projects, it shouldn't be such a big deal. Right? Right? And I also can just come back to this in a year when I'm smarter and just implement it differently. So let's do it. Let's bloody do it. So let's force our user to have to provide us the functions. So this will not be device definitions. This will be device MCU includes. And in this case, we include this file. And this file must provide 2 functions. 2 functions, please. Too many. Must disable all interrupts. Enable RQ. And this is very important. Must enable back all interrupts. This is such a messy design, but I'm forced to. I am forced. I'm not actually, but you get my point, right? Okay, so now everything else, every other break will be a break we can handle. We can handle by providing our structures. So let's add a struct that will be, I use this now in the modern day and age. Type def struct. This struct will be debug protocol implement. Debug protocol. Just debug protocol, it should be fine. Just debug protocol should be fine for now. Maybe I will name it later. So we need to provide two function pointers. Two function pointers that will be... Let me actually look up how to do it better. How to do it better. So it will be was. Oh, I see. Was. What? What is this syntax? I'm confused. What is a return value? Sure. But what is that? Pointer to const. What? Why is it inside the brackets? Whatever. I'm not fully understanding what I'm seeing, but at some point I wrote this code myself, so I might have understood what I'm doing back then, so I will trust myself on this. And here we need to provide two functions, and the first function will be send protocol message, which should take in what? It should take in what is this file? What is my correct file? Wait a second. No, it is a correct file. So should take this. This, please. And then another function pointer, which should of course be const. It will be handle protocol Rx. Should it be avoid? Maybe it should return something. Let me see what our current implementation returns. Like, does it return anything? It doesn't. And in this particular case, it means that it can stay void, and it has to take the message in the size. And this is quite universal. This is quite universal. Should they be const? This should definitely be const, and this then can be const as well. Do I make any changes to the pointer? Let declare it as const, and let's see if it breaks current build. Let's see if it breaks current build. It doesn't seem to break current build because this function doesn't have const qualifiers yet. Const and const. So let's see if it breaks now. No, it doesn't break it. So this function doesn't change the array at any point. So we are free to do what we've done, which is very nice. And this thing will make sure what. Oh, with this implementation, we can actually support multiple debug protocols running at the same time. Oh my. Oh my. Oh my. This is very nice, actually. But the functions will change. These functions will change because they will have to take a pointer to this now. So this will be the pointer protocol instance. And same thing here and here. Same thing here and here, actually. All of them. All of them be gone. So let's go to the implementation. Let's fix this implementation first. It will not be weak anymore. It will be strong. And how strong will it be? It will be rather strong. Like, actually, this function is not dependent on this. So go to hell. Instead, this function is very independent, and we just copy it. Build, it should build properly. Was. Oh no, it is protocol dependent. Hold on a second. No, it is protocol dependent. Fuck. Let me think. This is problematic. Somewhat. Not really, but annoying, rather. More annoying than problematic. It is hardware independent, but protocol dependent. And if it is protocol dependent, what do we do about it? I think we keep it inside the protocol, then not inside the general implementation, common implementation, right? This is unfortunate. Or is it? Or is it? What this function does? If there is no active stream, sure. If stream is activated but not active, sure. And if both of those are the case, we need to send a new stream message, which we don't know how to do, because sending new stream message is protocol dependent. So we have two solutions. One solution is for protocol to provide a way to send a message. Oh, actually, yes. There should be a way for protocol to provide a message. Wait a minute. Hold on a second. Hold on a second. So the message starts. So I will have to move this. My brain hurts. So what I can do is I can move only this line into a function pointer, or I can move both of them to a function pointer. And what is the better way to do it? Who can tell me? Who can tell me if one are better than the other one is better? Ooh. Ooh. Let's see. So what are pros and cons? Cons of this is actually this moment not only needs to be defined per protocol, but also called per protocol, because depending on the interface we are using, for example, UART or USB or whatever, the place at which this function will be called will be different. Whereas for two others, well, for one of them, this also will be different, but the second one will be absolutely unbothered by anything. So my thinking is that this is annoying. Okay, let's actually keep it here. So I take all of it back. It will be weak. I take it all back. It will be implemented here. So let it be here. But then to do and to do update description. because explaining why it is here and how it is used is very important. It is absolutely not obvious to anyone. Okay, software is hard. Architecture is hard. You probably know this, but I'm telling you again. Conflict types, of course they are. So let's keep fixing this because we provided this part here. And let's put it here. And now we can remove our dependence on the actual hardware and say send protocol message and do this. This is quite a big boy, but it should work. Quite a big boy indeed. So we remove this and now we are independent on the hardware. Mostly. We definitely are. Are we? What do you not like? Oh, I see. Oh, hold on a minute. What I've done? Oh, scheiße. Oopsie daisy. Now it should be fixed. No, I copied to the wrong place. No, wait, to the right place. Right? Hell. Conflict types. What? You message. What? The law. Okay, it works now. Q message. It works. And this handle RX. And we also have this. So let's fix all of them. And that's hold on a second. Q message. No, I made a mistake. This is a terrible mistake I've made. Holy cow. This should be there. And this should be oof. Oof. And this should be this. Ah. Like this. And now it breaks, but only breaks in this position. And this is very easy to fix, given what we've learned. And we've learned that we are gorgeous. So let's do it like this. Boom, bam, bam. Boom, stamps. Toof. Boom, bam, boom. I think I deleted the wrong thing. Build should be fixed. Yep. Okay. So this one is handle RX, and our RX handle will be just a single liner. It will just be a single liner, which will be protocol instance handle protocol RX. What does it take? Everything, I would imagine it takes everything like this. Right. For this to work, those should be constants. What do you not like? Too few arguments. How many arguments do you expect? But you expect to. What? Syntax error? What? The hell? Expected expression before this, but this is... Oh, I see. I am stupid. I am just stupid. And why is this broken? Too few arguments to debug ITFQ message. No, this is easily fixable. No, it isn't. Hold on a second. We get a looping schlooping dependency. This depends on this, and this depends on this. This is terrible. This is awful. If we call one in the other and the next one in this one. So how do we fix this? Actually, do we even need a function for this, like a separate function? I might as well just handle Rx like directly without it being in the bucket deals completely, like at all. Right? Like, what's the point of me having a single line call here? Like, there is no point. Especially given that this should be protocol independent. And this kind of implies that it's protocol dependent because this, as if we know a fixed place where this function should be called. So I vote in the voting circle of a single person, which is me, myself, and me again, to remove this. Thank you for listening, everyone. The call was made to remove this. And if the call was made to remove this, then this function will take a new argument, which will be this argument. Which will be this argument, so this will go away. Something still doesn't like something else, which is fine. And here we will add another argument, which is fine. We go here, we add it here. And now we provide it everywhere. Every bloody where. Okay, so let's see if it fixes things. It does, so we just need to do it like 20 more times. Just 20 more times. Easy enough. Dun, dun. 20 more times and we are golden. I see you, I see you. You have incorrect spacing, I see. 20 more times and we are golden. Let's see if we reduced number of errors. We did. So let's keep providing. Let's keep providing. And here you have an argument and you have an argument. Everyone have an argument. Sure. Arguments for everyone. Ah. Let's see, let's check. Also here. And here. And what else? Some spaces. And here, two places, of course, of course. Sure, sure. So this should fix everything, right? Wrong. What do you not like? Oh, because this function has to take this now. this function has to take an argument that will be this. And I need to move it to the weak implementation of this function as well. And now that it takes this argument, our re-implementation of it will be like this. Now everything should be fixed. No, something is still broken, it seems. Yes. But this brokerage is a usage brokerage. What else? Too few arguments in update message queue where sure. We need to define the new struct like a member of a new struct we created. So let's do just that. Let's just do that. I got lost. Well, and now this struct has a single member. Like, is this fine? Can this struct hold anything else? Let's see. Technically, actually, it can hold more things. And this is part of the way for us to make support for multiple protocols at the same time. So yes, a short redesign is in order. So let's continue redesigning it. And yes, we haven't tested the code for like 2 hours. So if it will work the first time, I will be amazed. So error log is a single one, com buffer is a single one, active stream. Should active stream be per instance of this object? For example, if we would like to send one active stream to UART and another one, for example, to CAN or USB. Does this make sense? Because if we use a single protocol, it will force us to use a single stream anyways. And will also remove a global. So yes, I believe this can be moved to the structure. What else can be moved to the structure? So you are dead. Total error count, no. Error log write index, no. Error log, no. Com buffers. Com buffers are a global concept and they are protocol independent, or are they? Should com buffers be also stored per debug thing? Should they be stored per debug instance? I'd say so, right? So this also makes sense to be moved to the struct. But error log should be the same because it stores errors for the device in general. So error log stays like this. Then, now, this means that those two should also go to H file, right? Oh. Should they also be a part of the struct? Because here I literally create an object. And every debug protocol have to have its own. So yes, this has to be moved as well here. So it has to be moved on top of this. Like this. And this has to become a type then. So it will not be static struct, it will be a type def struct type. Def struct txq. It will be then debug txq. And this will be here. Oh, this gets complicated as hell. But I also believe that this will be a huge boost to our implementations in the future. Like, it is a very important investment to make right now. And that is why we keep going, we keep working. So this is already a type that is used here. Sure. Will there ever be protocols that will not work with bytes but with something else? I don't think there is. Like, everything in the modern digital world can be converted to bytes, so it's absolutely normal to keep it like this. Okay? All right, so what we need to do is to provide one more argument here, which will be debug txq, which will be txq. Oof, to do write explainers. I need a 2-minute break to breathe some air before we will continue, because we are very close to end. But now I will press build and everything will break. Yes, and we will need to do quite a lot of home keeping. Is it the correct way to do it? Say it. And now type debug stream. What do you mean? And now type? It's in the same file. Oh, I see. Does make no sense. Because C is a single pass compiling language. You cannot have objects that use other objects over them higher than they are in the file. So let's build again. Expected specific qualifier before static. Yes, because this is not static anymore. It cannot be static anymore. Okay, and now all our errors here, and this will take a while to fix, but we will do it after a short break. And we keep on coming, and we keep on coming, and we keep on coming. So let's do this. Now, given the changes we've made, most of the things in the debug now have to take our struct as an argument. So let's start providing this as an argument then. First, we will work with the first one broken, which is this. Because now we register COM buffers not per device, but per debug protocol implementation. So we provide the argument here. Pointer, protocol. Actually, just protocol. Protocol instance is just too many letters. It's too much. Let's actually change it to protocol everywhere. Because protocol instance is just too many letters for nothing. Too many goddamn letters. And let's switch. Oof. Everything is broken because we changed so much. Okay, let's fix one at a time. One at a time, and we can go bigger here. Okay, let's do it. Let's do it. I'm not crazy. You're crazy. Sure. So, COM buffers will be part of this. Now, it will be protocol COM buffers. Maybe we can go call them just protocol buffers then. But that's kind of confusing because there is like things like protobuf and stuff, and the naming will collide. What does COM mean in the protocol COM buffer actually? Protocol COM buffer. What COM means? What did I mean by COM? Common? Combined? Combicorm? What? What did I mean by COM? Oh, by COM I mean communication. Communication. But why? COM stream is communication stream, but COM buffers don't make sense because buffers are not necessarily used for communication. So COM is not the letters I would like to use. And naming is hard. How do we make it easier? On our souls, debug buffers. Sure, whatever. Debug buffers. Just buffers. Just buffers. And now this function is not needed because get COM buffer is not important because COM buffer now is a part of the struct. And debug and register all COM buffers will have to take the debug register COM stream and register COM stream, sure communication stream. Get active COM stream will also not be needed because it is also a part of the struct now. Okay, this makes sense. So we kind of clean up actually. We're not only introducing new things. And this will be debug buffers. And this will be buffers. So it will be protocol buffers something. This actually reads nicer as well. Okay, this is very nice. Actually thinking about it. It becomes cleaner than it ever was. Let's keep going. So now protocol buffers Oops. Like this should fix it. Next free buffer index. Yep, this reads very well. Sure. So okay, like this. This will go here. Oops. Here. Right. And here. And it almost doesn't make code longer. Almost. Almost, as we are not here. Also, now thinking about it, should we then allow our different protocols to have different lengths of buffers allowed? I don't think so. I think it's already over complication at this point. It doesn't sound like much of a benefit to me. Too much of a niche improvement. And this should take protocol as an argument. Then, and that should be here. Debug and register all com buffers. It will be unregister all buffers, just buffers. Oh no! Com buffers now make sense because we have to put them together so that they can become communication buffers. Oh. But still. This also kind of makes sense, so whatever. But maybe I need to change the naming then. Because if we register buffers, because we can create buffer and not register it, and we can use it in the software, in the firmware, and it will work just fine. So we only register buffers if we would like to send them. So then it will become, oops, where the hell am I? No, it will become debug ITF because it's a part of the debug interface then. So it will be an ITF function. And this means that register com buffer, so it will be debug ITF. So interface and register buffer for the interface, and this makes much more sense then. Right? Now I see interface here and protocol here, and this is confusing. Fuck me. Whatever. Let's keep going with this idea, and maybe I will clean up more later. Reset buffer. Reset buffer is not a part of this at all. This is actually part of this at this point. Right? I think so. I genuinely think so. And now, this should be moved here. So this will solve this issue. So it is moved here. And this will provide error here, and it is not supposed to be here. Right? Yes. Yes, it is not. So, and as long as we don't include this file, this will not be checked, so it will not be triggered if anything fails this check, which is a correct behavior. Okay, we're getting closer. We're getting closer. Closer to the edge. Closer to the edge. I'm not saying I'm sorry. Hey. Yep, I'm so old. So, Debug interface register buffer. Debug reset buffer. So yes, this should be moved to here. And let's continue fixing stuff one step at a time. One step after another. So nothing new is broken, only this is broken. And this is broken because this thing doesn't know what stream instance is. And it's register com stream. And registering com stream it can be a function, but we can also do it not as a function. But if it is not as a function, there has to be some kind of instruction on how to do it properly. And these checks are technically have to be made. So let's keep it as a function, just provide an argument. So let's provide our protocol as an argument. Ah, what? Yeah. Let's provide our protocol. I think it's going to be called just comstream. Yes. So we provided an argument here. We need to provide it here as well. And now the stream instance we set is this, and this will be protocol com stream. And so protocol com stream will be set to a new value by this function when we register it. So this function is on the register com stream, should also take an argument. Our protocol as a parameter, and here it should be boom, pam, pam. And this should be bumps, bumps, and this should be dot. Oh, not dot. Was com stream. What? It should be a dot. Shouldn't it be? Com stream is a pointer. Oh, com stream is a pointer. Okay, sure. Sure, okay, whatever. So pointer of a pointer of a value. Sure. Pointer, pointer value. What else is broken? What else is broken? Send new message. Okay, we made a full circle, but it's nice that we haven't made a full circus. Haha. So like this. And here and here and like this. This part is fixed. Let's keep going. This part is fixed, so we have quite a few places in here. So this part is fixed then. Very nice. Oh, this function is fixed. All right. Here. This and that and what else? And this. And this. And that. Nice. This. That. This. Oof. TXQ requests. Okay. There is quite a chain of commands. C++, I see C++ in my C. Okay, so we don't have any errors here, but we have errors here. Quite a few of them, actually. Let's call it protocol. Mr. Protocol. Buffers, sure. Just buffers. Wait, what? Oh, I see. So this will have to change quite a bit, actually. Oof. This will have to change, actually, in an active way. In a very active way. So let's fix it one at a time. One step after the other. This, like that. Okay. I also need to update a stream description because we solved, I definitely remembered how my protocol works, but now we are at a pain point. So we would like to do what exactly? We would like to tell our master that information about our protocol buffers. So protocol dot buffers, like this, should actually suffice. This should suffice. And protocol dot buffers should be correct. Okay, and this will be a dot, of course, here as well. So this is fixed. Give me the next problem. So this will not be needed. Instead, what we will do is this dot and dot here, and this will be removed. Okay. Just protocol. Buffers like this and like that. This is fixed. I can just do this probably. No, I shouldn't. I really shouldn't. Was. This is fixed. So this is fixed. This is fixed. I'm very curious to see if it will work actually. Because this is quite a workload of changes. So active stream, but this function doesn't exist anymore, and this is why we remove this. This should be correct now, and this should be like this, and this should be com stream. Just protocol here. Does it make sense? It does. It actually does. So we keep going. And this should be com stream. So we can do like this. Okay, all right. Sure, of course. Let's see, it works. Everything looks clean and nice here. Yes, this looks like a pain in the butt, and it is a pain in the butt because the initial design wasn't very nice, but after we are finished with this, it will be so pleasant to work with. I promise. but we'll probably have quite a bit of debugging to do before it works. Active stream. So this. Entry field types. Active. What the hell is this function actually? Oh no, this is what? Oh no, this is correct. This is correct. This is definitely correct. This is correct. And this is fixed now. This should be removed. So this should be removed as well. This should be changed. We do. This is okay. This is all right. All these checks make sense still. We remove this. We remove this as well. And instead we use, also we remove this and we go here. No, we don't go there. We go here. And this is already fixed correctly. Yes. Yes, it does. It is. Eat whatever you please. Hold on a second. Activated stream. It should be com stream. Yes, this is the way. And if it is active, we send the message. We send our message. And this should be all of them. So we have another error, which is a call error. Oof, we fixed everything obvious. And now we should actually do what? Do what exactly? We will try to test it now. Or should we? Let me think about it for a moment. Let me think about it for a moment. I definitely need to write down a few thoughts about the architecture. But after that, yes, we will test it. We will finally go and test it, and it most likely will break, and we will debug it for an hour or more. But it is what it is. It is a part of the way to improvement, part of the way to greatness, part of the way to success we are taking. Okay. Unused variables, of course, because now this function was renamed to be debug protocol UART. It has to take a protocol, of course. But first things first, which is write down the to-dos. So conceptual to-dos. To-do. Move UART protocol. Move debug UART protocol to dependencies and document its requirements, like what functions must be present for it to work. Probably will be a common location, actually question mark, because if it's a common location, at least in CubeIDE, and we store C files there, all C files will be added to the build, which means all H files will be added to the build, which means all errors will be added all the time. So I think after thinking about it for 31 seconds, I decided that protocols should be split into separate folders to not cause unnecessary error checks and failures. Okay, then to do. What else do we need to do? What else do we need to do to make it work in a useful way for the future myself and for whatever anyone who may want to have access to this code? Yes, move all Python scripts that are part of the protocol together with the protocol for convenience of use and extension. Because I have quite a library of Python files that's supposed to work with this, but they are kind of together with all the other files. And also there will be a Python to do to make sure and that Python files are not blockers for a possible usage of the protocol with other data transfers. So next, what do we have next? What do we need to do after this? What more do I want from myself? I think that's about it. And now how we will test it? How will we test it? Oof. Oof. What was that? So, to test it, set up peripherals. Okay, test one. Set up peripherals and make sure why did it enable now? Set up peripherals and make sure that saving error log works. This is the most important test. If it works, everything else will work eventually. And this test that was not broken in any way because error log is still global. So this path of our debug protocol is the least changed of everything we've done. So if we make this work, everything else will come with time. Then test 2 add to debug buffers and make sure I can save them. Test 3 add a debug stream and make sure I can save it. Then will be to do, which will be update debugging examples, which will be a pain in the butt to do. It's a lot of work, but it will be probably done tomorrow. It will be a lot of manual work, but it should be kind of relaxing, but also kind of time consuming. So what else do I need to do? It would be nice to test 2 different protocols, but it's kind of hard now, so I would like to not do it now. What else should we do? What should we do? I think this is it. I think we need to do this, and we can be happy individuals going to bed. Depending on when we leave, we might as well not go to bed, but whatever. but whatever. Forever and ever. So, how do we do this? We have this, which enables our UART. We need to attach our UART connector, USB UART converter. So let's turn the power off. Let's attach our converter. And let's turn the lights off as well. We need to move closer to USB. Extend there, because this wire is very short. Like that. And let's make sure that our shaft can move still. So we are attached. And now let's continue setting up. So this is implemented now. And also it means that UART interrupts are running actively. So if they are running actively, which they are, I hope they are correct, then we do what? Let's see. We don't do anything here for now. We do this. So we need to create protocol here. So our debug protocol, let's say UART protocol equals to what exactly? So buffers. We don't need to set it up to anything because it's a struct, just exists. And actually, no, hold on a second. Buffers and debug buffers. Let's set it to, because it is a struct in itself. So buffer values. Don't remember how to use it. I will need to see an example. But buffers are. Why are you not happy? Hello? You are showing me something incorrect. UART protocol. Why are you making such a big ident? Okay, whatever. It should be equals to void pointer to 0. We don't provide a com stream now. Void pointer to 0. Okay, this should be this, comma, txq. Okay, where have we stored txq before? txq. txq. It's just an object, so it's already predefined. Active queue size, so all of them can be completely empty, sure. They all can be defaulted to 0. Nothing bad will happen from that. Can buffers be all put to 0? So this is a pointer to buffers values that can be put to 0. So we need to specify this then as a pointer to 0, not a 0 directly. So it will be buffers, which will be equals to, my God, brother, equals to void pointer to 0. Like this. So this is important. What do you not like about it? It is correct, no? Oh, this is what you not like, sure. That makes sense. That makes a lot of sense. So do we need to, and what is that? Missing braces around initializer. Was. We don't. Do we? We don't. Do we? We don't. Okay. So this can be set to 0, 0. Oh, I haven't still understand what this is. But I would assume it's going to be set to 0. So do we need to set anything else to something? ComStream is reset, TXQ is independent, and send protocol message is what we need to initialize absolutely for sure. Send protocol message will be equals to debug. Actually, what will it be? What it was before? Oh, and I don't remember. I will have to look up my Git history. This is it. So what was that before this? Let's see our function to send. Add value to the buffer. Okay. Wait, what? No, I don't need to add value to the buffer. I need... Oh, no, this should be here. You don't look as that I have so many files. This is as intended. This is as intended. Everything is absolutely fine. Nothing is gonna to be broken, I promise. So here, debug UART send message DMA. It was sure. Like this. Should be all right. Right? No? What do you want from me? But I don't think there is a mistake anywhere here, right? I hope so. Okay, whatever. So let's fix this. It will be an address of this value, and those will be this way. This can be gone. It is set DMA, sure. And we also commented out this one. Update message queue. So RUART protocol. No. We should just keep this function. It's actually functional. We just need to provide this. We need to provide an address to our UART protocol. Very nice, very nice. And I think that this is all. We just need to make sure no errors. Holy cow. Okay, this looks promising and I hope it will work. So let's start something. Let's put an error deliberately into our error log so that we can read something. Log error 312, whatever, 3 times. Now, what I need to do is to go and find my, no, I don't need to go and find them. They are here, somewhere here. Where exactly? Scripts, no. Was? Oh, we have a separate repository for this. This is unfortunate. Unfortunate, but fine. We can work with this. Let me think. Now I also think that working with Python will be also a pain later when we need to clean all of it up. But for now, I need to find my scripts that I'm doing off screen for now. Project templates, graphics, advanced cloud systems testing. Pass. What is that? What is this? One moment. One moment. Okay, again. Oh no. Where are my scripts actually? I don't remember. Oh, it is in this project. It's just in a different location. Sure. Okay. Here are our scripts. There are quite a few of them. Let's see. Python, and we need to scan COM ports. So we have USB art on COM10. So sure, let me turn on the power and let's run what? So COM, save, debug buffers, no, error log, yes, and the COM will be COM10. Was, oh, Python COM, save, error, COM10. Device is not responding. Make sure that connect device supports debug protocol. Okay, so we have an error, but nothing crashed. So something is happening. Oh, but we haven't even flashed the firmware yet. So let's do it. Of course. We haven't even flashed the firmware. So of course it doesn't work. So maybe it will work the first time. Who knows? Okay. So let's run it. Will the calibration work? It does work. So we are in debug mode if we need it. And let's wait for the calibration to finish. Everything should be all right. Will the motor spin? Motor? It spins. It works! It just worked the first time! No fucking way. It worked the first time. I was just changing the code for like 2.5 hours without testing. So error log 17706. This one. Yes, it worked. It saved it. It worked. It just worked. Such a pleasant feeling, actually. My God. It just works. Yes. It just works, and I can save this. Okay. So this was incredibly fast. Way faster than I expected this will be. It just worked the first time. It never happens on this stream. Especially after 2.5 hours of just like changing the code all over the place. Holy cow. This is so satisfying. Okay. I actually can't believe it. But whatever, let's keep testing. So this test already passed. So we are done here. Big W. So W in the chat. For myself, let me do self-encouragement. So I definitely will need to add a W emote later on. Okay. So now, other tests. So we need to add debug buffers. We need to fill them with values of sorts. And we need to test if this functionality works, because this was changed more significantly. So let's do it. Let's just add 2 debug buffers. So let's say right here, we do debug buffer, no, U32 buffer, U32 B1. And let's make it like this. Let's just, let's actually make them different types. So let's call it buff. This will be float. And now let's fill them with values and let's register both of them. So how do we do this? We call debug ITF register buffers. UART protocol buffer pointer. It is address to our user2 buff. And buffer type is type. Let me see what I am. What do I supposed to put there? Oh, I see. It will be U32 type O. Typo, hey. Okay, and the same here, but with F32. We registered them. Let's fill them with values. So for let's use uint rather equals 0. I less than debug buffer local debug error no debug buffer size I plus equals 1, and let's just put our user2 buff. Okay, add a debug, add value u32, this buffer, and value will be I plus 1. Like this. And let's do the same for float value. So this will be, and this will be a float conversion of I. And let's say multiplied by 0.25. So we will fill them. We already registered them. Order is not important here. And that should be it. After this, we should be able to just read them. Something is incorrect here. Implicit conversion. Hold on a second. Oh, yes, of course.
Daz is now following.
Thank you, Mr. Daz, for following. I'm glad you're enjoying my struggles. So this is like this. And now let's flash it again. We don't want to convert to double, of course, at any point. And let's run it. Oop. Hold on a second. I think we got infinite loop. What? Again? Okay. Okay. I'm pressing too many buttons. Again. Let me go again. So we are flashing. We are connected. We are here. We run. We have infinite loop. What is happening? Are we out of bounds? What is the value of this? Actually, let me put a test point here. Interesting. We have an error, an infinite loop handler. Let's see, we run, we get here. Why do we have? Okay, I see. So at this point in time, what is this value? 64. Why is it 64? Sure, why not? So I should be able to see here 64 values, right? No, I see here 2000. Why do I see here 2000? Because they should be defined in an H file, right? Hold on a second. They should be defined here at some point. Yes, 2000, which is quite a bit, but whatever. Okay, sure. They should be redefined then in main. So where was I? Where is my main? Here. So this should work fine, and this should work fine. So we go inside this. Okay, we are breaking in the loop. And why are we breaking inside the loop? Okay, let's do again. So we were breaking inside the integer loop, not inside the float loop that I thought. So we need to go inside and see what breaks there. Sure, sounds easy enough. Let's go again. Sounds easy enough. So we go here, we jump in, and jump in. So what is wrong here? So fields, jump, okay. And buffer size here is equals to what? 64, but it shouldn't be 64. Okay, we jump in, we jump, and we return. What? Oh, I see. I am an idiot. I see. I am such a dumbass. I see now. Now I see the truth. Rather not the truth, but the false of my. Oh, I'm such a dumbass, actually. Let's make them global, because if we define them here, they are not reset to 0 because they are defined on stack. And to make them 0 by default, we need to move them here. And I believe that this will just work, because we had garbage there. And this garbage might have as well just do what? Fields. Fields are to values. Sure. Run. Yes, just runs. Okay, I'm just a dumbass. I either should have zeroed alt values or I should have moved them to the global, which now it works. Our motor calibrates, I would imagine. Does it? Motor should spin any moment. Yes, motor works. Now let's go to our Python scripts. Where are they? So let's see if our error log saves. It saves. It should have the same value, 3 of these values. And now let's see if our buffers save. So com save com flaw plus python com save debug buffers and odd comport then. It worked. It worked. So buffer log 77706 out here. What? 77706, this one. So, and it works, but for whatever reason, it says 1000 here and whatever is the value here, but then it's 1, 2, 3, and this is multiplied by 25. So it's saved, it worked. It actually bloody worked. No way that code that I was changing for like 2.5 hours just works the first time. No bloody way. But why do we have 1000 as our first save value? So let's see if we have an issue in the code. Let's go to a better view. So we provided here a protocol or buffer and the type, not here, we just call this function and we provide our buffer, which should be empty at this point as the first iteration. And we would like to save 1 as the first one. But for whatever reason, we don't save 1. Actually, let's see the state of the buffers after the call. So let's say before we read the code, let's see the state of the buffers. Let's see the state of the buffers. Let's run it, and we hit the breakpoint. Let's see variables. What? We don't have anything? Oh, because those are global, of course. So we can see them in the live expressions. So let's open our values in the first 100. Let's open the first 100 of our values. Now they are correct. So this is 1. So the issue is on the Python side. Then, so this correctly starts with 1. And I would imagine the second one correctly starts with 0.25. F32 buff. Let's see the values first 100. Yes, it starts with 0. Of course, because I haven't done +1. So this is correct. And let's make the code continue running. And let's go to our scripts. Let's actually clean all of this. I don't think I need any of this. If anything was needed, it was definitely saved into the GitHub. And here, let's read our buffers. Okay, and they saved into 776110, this one. No, it still has some garbage here. So it is on the Python side then. But how many entrances do we have? So the last value is supposed to be in our version 1001. It's not even 1000. So we have 1000 readings. Or maybe the issue is on the sending side. How do we send it actually? There is definitely an issue somewhere with an indexation. We miss an index by 1 probably at some point. So let's just figure out where exactly. Let's just figure out where exactly do we do this. So let's remove this. So we clarified and made sure that at this stage in the code, the buffers contain correct values. So the only way they can be mistreated is when we send them. And we send them in the Rx response. So let's open our Rx response, which is a bit higher here. So here we are in Rx response. So let's open it fully. And we are supposed to receive something related to debug buffers. So read buffer properties. We read them correctly because they were correctly displayed in our Python log. Then read one of buffers at a time. And we read both of them correctly in correct order. But when we read them in correct order, we don't read them at correct. We don't provide the correct values. So requested index is an index of a buffer, not an index of the message. So this is correct. Oh, then if requested index is incorrect, we just say that we cannot provide it, or we say that yes, we can provide this, and now we prepare our message. So we set our buffer type and we set the pointer to the buffer value. Okay. I can actually put a breakpoint here and just call our Python script again, because I can save these buffers as many times as I want during the runtime. So let's just call it again. So we are stopped here. We are stopped here, and now let's see what value does this pointer have. So it's buffers, protocol, buffers, buffer type 3 and 1, this is correct, and buffer values requested index. Oh, how do I check it? How do I check what is stored there? How do I do this? Because this is a pointer. And the pointer is actually, I think I can just read this value again. Nope. Okay. Values, first 100 values, they are correct. They are correctly provided. So there is no issue here. No issue in the values themselves. So buffer, buffer types, buffer values. How do I get buffer values when I create buffers? So let's go and see the registration code for the buffers, which should be the fastest way to find it is through the registration function. So we register our buffers here. So we register a buffer by next free buffer sure. If we are full, we skip, but we are not full. Buffer pointer is not 0, and it is of correct type. So then we set a type, and we set a pointer to the buffer. What? Buffer values, buffer pointer. Oh, I see now. I see the issue. Do I see the issue? Hold on a second. Yes, I see the issue now. Oh, now it makes sense. Oh, hold on a second. Now it makes so much sense. I know why it's broken because of our changes we made today. This is actually such a nice bug, such a tricky bug. And the bug is, oh, it's so beautiful. It's beautiful in a way, like, it's kind of beautiful. So let me, oh, I'm getting lost. Let me find a file. So the beauty of this bug is that this is a change. This is a fix for this bug. Moving like this. This is a fix. And the issue is that we would like to provide void pointers. We can fix it actually differently, but I think that I don't rely on this orientation for now. And why was I doing this orientation? Because I was trying to also use void pointers in a different way. So holy cow, C, a deep C. So this will be the fix and it should work now. So let's try it and let's actually remove our breakpoint. This is such a nice bug actually. We just introduced. Okay. So let's run it. It should not break anything. It doesn't. So let's go to our Python scripts. And let's make sure that we can read our error log. We can. Let's check our error log that we have no errors. 6218. Yes, we don't have any additional errors. And now let's read our debug buffers. We have read them. 62197 buffers. This one, yes, fixed. Fixed! Actually, a very interesting bug to have. And now the number of values is correct and the values themselves are correct. So very nice, very beautiful solution and problem. So this is done. And now we need to try to test the debug stream. So let's do it. We can keep this code. Debug buffers are not heavy on the processing at all. They are not introducing any overheads to anything unless we do something with them. So what do we do then? Oh, I actually should do it like this. F. But I will do it later. So just add physical constant for readability. Okay. So stream. How do we do the stream? And for stream, we need to remember what to do. So the stream is provided. How exactly? Have a pointer. Oh, I think we actually implemented it incorrectly. I think we implemented the stream, the debug stream incorrectly. So, because we implemented it as a pointer, but we have no way of creating a stream out of thin air. Or actually, did we make it incorrectly? Maybe we want a behavior when we can use multiple debug streams on a single protocol, right? So this can actually be, because we left the registration function. Yes, let's actually open the file, each file, and let's see. So debug streams, no, update com stream, and oh, so we don't have any functionality other than this. So we removed the, registered buffer and unregistered buffer. So the stream is now with this implementation by default enabled. So we don't have a registration for the stream, which means actually it still allows multiple streams. We'll just need to copy them as separate objects. So it's fine. But it means that this struct is incorrect, and the struct is incorrect because this should be not a pointer. This should be a structure directly, and we need to define it properly. So let's do this. Let's do this correctly. So to do this correctly, we should go to our main, and we should go to our definitions, and here our stream, we should define the values for it. And how do we define the values for it? I hate that autocomplete doesn't work here, but whatever. Oh, this will be actually kind of pain in the ass. We need to specify many things. Let's say we would like to send a similar message just at the stream. So uint32 and f32. So our entry field types will be equals to u32 type and f32 type. Okay, so this is first thing we need to provide to our stream. So what else do we need to provide to our stream? We need to provide entry size, entry field count, and entry field count is 1 in our case, right? Entry field count was. Okay, autocomplete doesn't work. In our case, it's 2 because we only have 2 values here. Actually, let me read my example again, just for the sake of it. We would like to send 5. Okay, I can move it slightly here for better readability. One moment, short self break. Okay, everything is fine. So we would like to send 5 points of this type. Every message will have 5 entries. Okay, so then the entry count is 1. No, entry fields. What? Oh, entries per message count will be 1. Okay. But let me continue reading. Do not send message too often, or whatever the reason is. Sure. In this situation, all 5 points will be by default say separate 5 lines. Sure. In this case, our message will have message bytes. Sure, message bytes is easy to set. We can just calculate it. Message byte size will be 8 because we sent U32 and F32. So let's see. Okay. No alignment issues. Entries per message will be entries per message count will be 1 in our case, and entry fields will be correctly set up, and entry fields count will be 2. Perfect. So instruction works fine. Do we need to set up anything else? Or we need to also provide a message that will be sent. So, and the message will be sent, let's say, struct test, no, it will be just struct you int 32t u32 field and this, and you int, no, float f32 field, and it will be test struct stream, no, test stream struct. Okay, so we provide the message as pointer to this struct, right? What is the order? The order is correct, so we can allow ourselves to do it like this. Scary C trick that you can do it this way, and it will work absolutely correctly. Don't do it at home unless you know what you're doing. So timeout, let's say timeout in milliseconds. Time out milliseconds, let's say it will be thousands. What else? This is done. This is done. ID, let's say ID equals to 5, 4, whatever. Entry fields count is active is set to 0 because it is never active by default. Sent to 0 and entry field types. So we set up our stream correctly. We don't need to register anything. Actually, do we need to do anything at all with new system? We have a single stream related function. Do we even need to have an stream is active now? Because this field now is not used anywhere, right? Hold on a second. Hold on a second. So it is used in 4 places, and let's see. This is an register com stream. Oh, wait, we have the register functions. But do we need them? So register stream. Okay, how was stream is active determined before? Oh, we can no. So it is set by 1 by the protocol itself. Okay, this makes lots of sense. So registration is not needed, but this flag is needed. Okay, sure. This makes a lot of sense. Update com stream is a function we will have to call, of course, sure. And here, I do believe that it is safe to remove both of them. Because first of all, we remove them here. And second of all, they do absolutely nothing at current implementation. And if we will need this behavior later, we can just re-implement it. So removed builds should not break because they were not used anywhere. Oh, build breaks. Was. Why did my build break actually? What is going on? Binary. Oh, now that it is not a pointer, it broke all the implementations. So actually, for the sake of my sanity today, let's keep it as a pointer. Let's actually keep it as a pointer because it breaks so many things. And also having it as a pointer helps in a way. It helps to allow us to, on the other hand, should we? I guess so. Well, let's keep it as a pointer. I decided. Let's keep it as a pointer, actually. So then we go here. Oh, we will need to revert so many changes. Not that many, actually. Pointer, but something will break. Of course, this will break because at this point, oh no. This. What? Field name not initialized. Yes. Because this now makes no sense because we need to provide the debug.com stream as a separate data type, which will be test stream. And we can just copy all of those here. Just offset them a bit. And here we provide an address to this value. So now it will build, now it will cannot convert, of course, because this should be address. Okay. Looks decent. And now we need to update the values there. So we need to send something usable. And let's send. So how will we do this? This is actually very easy to do. This is so easy to do, actually. Did my motor broke? Oh, the motor is broken for whatever reason. Hello? This is definitely an incorrect behavior on the motor. Huh. Did my protocol break the motor? Do we have any errors? Can we see if we have any errors? We don't have any additional errors, so something is happening. Okay, but I'm not in the mood to debug it right now. I'm in the mood to finish ComStream and debug the motor issues after this. So what we need to do here to make it work is take. Oh, I remember what else I should test. Test for, but this will require script updates, so it will require a lot of work. Test for test multi-target communication, meaning debug protocol plus completely independent protocol using the same URL. And we have a W here. So let's see, we need to finish just a little bit of work to make this work. So let's say we will update this in the position loop for now, just as an example. Our position loop, let's just find it. Position loop. Yeah. Let's just assign something to these values. What? Oh, yes, it's correct. Plus equals 0.2 and u value plus equals 1. And update what is the function name actually debug. It should be itf update stream. So this should be debug itf fit all the other naming conventions. And we also need to rename this in the UART. in the UART implementation, and UART implementation is here. I don't like it, but whatever. Not now, one problem at a time. Okay. So this is it. And we need to call it in main right here. And this, oh, this is all we need to do? Oh, this is so easy. Okay, so let's flash it. And let's see if it works and if it broke anything else at any point. So let's run it. Let's see if motor calibrates correctly. Okay, and now please rotate back. Pretty please. Okay, so motor works. And now let's go to our Python and let's start with error log. Error log is saved. 63266. So correct. Let's check buffers. Buffers are saved. They look correct and as expected. And now let's see if stream works. Python com save stream at com10. It works. It works. And now let's cancel it and let's see what we saved. So stream ID4 log and values just incrementing as expected. So streaming also works. So all the bug features are now working with our new implementations that can allow us to use both multiple protocols at the same time and also to make it protocol independent. So it's a huge success. Hooray! Celebrate everyone. This was quite an undertaking and it was very successful. Very, very successful. So now, what now? Now we should understand what's happening to the motor actually, but maybe not today. So this was a huge, huge, huge improvement. There is still work to do, and tomorrow we will work on the implementation of examples, because things like this, when you implement something complicated and something very important to the quality of your system, to the quality of your code, to the quality of your controls when you work with control systems, things like this must be documented. You cannot just leave them as they are. So this is what we will probably do tomorrow. On stream, we will make examples, we will make documentation for this. And I think I will stop for today. This was great. I'm quite new, but just wanted to say you are very inspiring. I've been enjoying the stream and watch. Keep up the good work. Thank you, Mr. Das. Thank you so much. I hope I'm inspiring you in the right direction, because bare metal is kind of complicated, but it's also very satisfying and it's very forcing to learn. So I'm very happy that you are enjoying this. And I hope I will provide more entertainment and more enjoyment and more knowledge in the future. And if you have any questions, feel free to ask. So, but we've done our tasks for today. So I don't plan to do anything else today unless people have questions. I can answer questions before I finish. But other than that, I think today was very successful. Do anyone in the chat has any questions? Looking forward to it. Sure, I appreciate it a lot, actually. Okay, I think no one has any questions for now. So see you all in the next one, which should be tomorrow. Yes, everyone enjoy the rest of your days and stay safe, and see you tomorrow. Bye-bye.